Good evening. Welcome for today's session. So, if my audio and video is clear, I request the students to just raise the hand so that we can start our session for today. If audio and video is clear, just raise the hand, sir. We can start our session. Okay. So now let us just revise what are the topics that we all discussed in the last class, and then we can move for today's session. In the last class, we are discussing about a differential relay. In the last class, we have started discussion regarding differential relay. So, where do you use the differential relay, sir? Differential relay is used in production of what? Alternator, transformer, and bus bar. Okay. Differential relay will be operated when, sir, what is the condition that must be satisfied for operation of the differential relay? What condition must be satisfied for operation of differential relay? Differential relay will be operated when the vector difference between two similar electrical quantities exceeds its set value. Okay. Differential relay will be operated when the vector difference between two similar electrical quantities exceeds its set value. Differential relay is said to operate. What are the basic requirements that are to be satisfied for operation of differential relay? What basic requirements are to be satisfied here? The basic requirements are like this. We require two similar electrical quantities. That means either you require two currents or two voltages to compare. Okay, here we require at least two similar electrical quantities. That means you require either two currents or two voltages, and there should be 180 degrees phase shift between those two quantities. Those two quantities must be out of phase by how much? 180 degrees. So what are the basic requirements? We require two similar electrical quantities, and there should be how much phase difference? 180 degrees phase shift between those two quantities. These are the two basic requirements that are to be satisfied in case of what? Differential protection. Okay. So once you satisfy these basic requirements, here we can compare two currents or two voltages. Okay. So here I have shown that generally the current differential protection is mostly used. The current differential protection is mostly used. So for implementing current differential protection, suppose this is the electrical equipment which is to be protected. This is the electrical equipment which is to be protected. It may be a transformer or alternator or a bus bar, whatever it may be, which is desired to be protected. So for implementing current differential protection, what we are doing here, we are connecting the CTs on either side of the electrical equipment which is to be protected. Here we are connecting the CTs on either side of the electrical equipment which is to be protected for comparing the currents. Here the CTs primaries will be connected in series with the line. Here CT primaries will be connected in series with the line, but the CT secondaries are connected by means of what wires? Pilot wires. The CT secondaries are connected by means of pilot wires. Okay. Here on secondary side, there is only communication required. There is no power transfer that is required on secondary side. Only communication is required. Okay. So this differential protection is a unit selective protection. Differential protection is a unit selective protection. So if the fault takes place within its zone only, the relay should operate. If the short circuit fault takes place within its zone only, the relay should operate. If the fault takes place outside the zone, here I have shown throw fault. Throw fault means fault is outside the zone. So if the fault takes place outside the zone, the relay should not operate. The relay should not operate because it is a unit selective relay. Okay. So here if you observe, differential relay is a unit selective relay. It should operate only for the faults which are taking place within its zone. It should not operate for the faults outside its zone. Okay. So here pilot means communication channel. Pilot means what? Communication channel. There are three types: wire pilots, carrier current communication pilots and microwave pilots. Wire pilots, carrier current communication pilots, and microwave pilots. There are three types. Okay, so wire pilots are feasible up to 10 kilometers length. Wire pilots are feasible up to what? 10 kilometers length. Up to 10-kilometer length, we can use these wire pilots. They operate at what frequency? Supply frequency only, 50 hertz frequency. But second one is carrier current communication. Carrier current communication. Here, carrier current communication, what you will do on the same power line, what you will do, we will transmit a high frequency communication signal. High frequency communication signal is being transmitted. Okay. And microwave, as of now, it is not used in cell phone communication. We will be using this microwave. Cost will be also more. Okay. Wire points are made slightly capacitive in nature so that voltage get easily balanced. Now, if we observe, as this differential relay should not operate for the faults which are taking place outside the zone because it is a unit selective relay. But this relay may operate for the faults which are taking place outside the zone due to dissimilar magnetization characteristics. Due to dissimilar magnetization characteristics. Dissimilar magnetization characteristics means what? One of the CT core may saturate. Dissimilar magnetization characteristics means what? One of the CT core may saturate earlier than the other. Dissimilar magnetization characteristic means one of the CT core may saturate earlier than the other. So here I have shown two CTs, CT1 and CT2. CT2 is saturating fast when compared to CT1. So what happens? Even the fault is taking place outside the zone. Due to the saturation of the CT core, there may be current through the relay and the relay may operate. There may be current through the relay and the relay may operate. Okay. So if the CTs are not having similar magnetization characteristic, one of the CT core saturates earlier than the other and results in relay operation for the faults outside the zone, which is not desired. It is not desired. To avoid this, what we'll use? We will use percentage biased relay or percentage differential relay. To avoid this, what we will use, sir? Percentage biased relay or percentage differential relay we will be using. Okay. Now, let us go for today's discussion. Sorry. Just wait. Let us start the analysis for today's class. Just a minute. Okay, right. Now, let us discuss what we mean by percentage biased relay or percentage differential relay. Percentage biased relay or percentage differential relay. Differential relay. Okay. So what do you mean by that? So up to now we have discussed, suppose if you want to protect this electrical equipment, this is the electrical equipment which is to be protected by using percentage differential relay. Okay. So what you will do here, we will connect the CTs. Here we will connect the CTs on either side of the electrical equipment which is to be protected. Here we will be connecting what? CTs. Here this is CT1 and this is CT2. CT1 and CT2 are connected on either side of the electrical equipment. And the CT secondaries are connected by means of what? Pilot wires. Here the CT secondaries are connected by means of pilot wires. And relay coil is connected exactly at the middle here. Relay coil is connected exactly at the middle. So let the relay coil number of turns be N0. Relay coil number of turns be N0. So this was the differential relay that we have discussed up to now. But what do you mean by percentage biased relay or percentage differential relay? Apart from this relay operating coil, here we will be using an additional restraining coil. You will be using what? An additional restraining coil is connected on either side of the relay coil. What will be using, sir? Restraining coil is being used. Now let us observe. Here we will be connecting what? Restraining coil on either side of the relay coil. So this is half of the restraining coil is connected on this side and the other half is connected on the other side, NR by 2 and NR by 2. This is nothing but restraining coil. Okay. So restraining coil. So this restraining coil will develop the additional restraining force to restrict the operation for the fault which is taking place outside the zone. Which is taking place fault outside the zone. The relay should not operate. The relay should not operate. To restrict that, we'll be connecting an additional restraining coil on either side of the relay coil. So this is known as percentage biased relay or percentage differential relay. So what we can make a point in case of percentage biased relay or percentage biased relay or percentage differential relay, an additional restraining coil is connected on either side of relay coil, relay coil. Okay, to restrict the operation the operation of relay for faults outside its zone, for faults outside zone. Okay, for the faults outside the zone, to restrict that, what we are connecting here, we will be connecting an additional restraining coil. Here we will be connecting what? An additional restraining coil apart from the relay operating coil. On either side of the relay coil we will be connecting this. Okay, now how we can mathematically analyze, prove that by connecting this restraining coil, the operation of the relay for the fault outside the zone is restricted. Okay, now here N naught is number of turns on relay coil and NR is the number of turns on restraining coil. NR be the number of turns on the restraining coil. So what about the operating force? So operating force F naught is directly proportional to what here? F naught is directly proportional to square of the MMF. So during normal condition, what will be the current through this relay coil? This relay coil carries current of what? So here primary side current is I1, here the step down current I1, here the primary side current is I2, here you have the step down current of I2. So what will be the current through the relay coil? I1 minus I2 is the current through the relay coil during normal condition. And this half carries I1 and this half carries I2. Half of the restraining coil carries I1 and other half carries I2 current. Now, F naught is directly proportional to what? Square of the MMF in this case of relays. N naught is the number of turns. MMF is what? Number of turns multiplied with current. I1 minus I2 whole square. Okay. Now, what about the restraining force? Restraining force is directly proportional to square of the MMF. So NR by 2, half of the restraining coil will carry what? I1 current, and the other half NR by 2 into I2 current, So now what about the restraining force? Restraining force is directly proportional to NR by 2 into I1 plus I2, I1 plus I2 whole square. I1 plus I2 whole square. So what is your observation? F naught is directly proportional to I1 minus I2 square. F naught is directly proportional to what here? I1 minus I2 square. And Fr is directly proportional to what? I1 plus I2 square. So during normal operation, during normal condition, this is what, during which conditions are this? This is during normal condition. This is during normal condition I am analyzing here. So which will be more, restraining force or operating force? Restraining force is I1 plus I2 whole square. This is I1 minus I2 whole square. No doubt we will develop the restraining force is greater than the operating force, and relay will not operate. Relay will not operate. Relay will not operate for the fault outside the zone. So if the fault is taking place outside the zone, the relay will not operate for the fault. The relay will not operate for the fault. Okay, understood my point? Fault is taking place outside its zone, so the relay will not operate. So here the operation of the relay is restricted by what? Connecting the restraining coil in addition to the relay operating coil. This is known as what? Percentage biased relay or percentage differential relay. Now let us check whether this relay operates for the fault if the fault takes place within its zone or not. So what we will do? we will we will observe whether this relay will operate for the faults within the zone or not. Now we need to check that. Okay, so if the fault is taking place within its zone, the relay is operating or not. Let us observe. Now let us consider an interconnected system. There are two types of systems now: interconnected system and radial system. Now let us consider interconnected system. Interconnected system. Interconnected system. Fault within the zone. Fault within the zone. Within zone. Okay. Interconnected system, fault within the zone. We should observe whether the relay operates or not. So during normal condition, these are the currents. This is source S1 and source S2. Suppose if you observe, these are the currents during what condition? Normal condition. Now let us observe by considering the short circuit condition. If you consider the short circuit condition, how the relay behaves. Now let us analyze here. So suppose if the short circuit is taking place within the zone in case of interconnected system. If the short circuit is taking place within the zone in case of interconnected system. So if the short circuit fault is taking place within the zone, what happens? Normally this is the I2 current, but now the I2 current gets reversed here. I2 current gets reversed. I2 current gets reversed. I2 current gets reverse. So observe here, I2 current due to the fault get reversed. So if the primary side current is reversed, automatically the current on secondary side also reverses. Current on secondary side also reverses. So what is the relay coil current during fault now? It is changed to I1 plus I2. It is changed to what? I1 plus I2. During normal condition, it is I1 minus I2. Now due to fault, it is what? I1 plus I2. So due to fault, what happens? Due to fault, what is the operating force? F naught directly proportional to square of the mmf. Square of the mmf. What is mmf here? Number of turns multiplied with current. N naught into I1 plus I2 whole square. I1 plus I2 whole square. N naught into I1 plus I2 whole square. This is the operating force expression. Okay. Now what about the restraining force expression? Now Fr is directly proportional to 1/2 is carrying I1 current, Nr by 2 into I1. I1 current does not change. But which current has reversed? I2 current reversed due to fault. Reversed due to fault. Due to fault. Within the zone or outside the zone? Within the zone. So now Nr by 2 into I2. Nr by 2 into I2 whole square. Now force is directly proportional to what? Nr by 2 into I1 minus I2. I1 minus I2 whole square. Now observe, F naught is directly proportional to I1 plus I2 square. F naught is directly proportional to I1 plus I2 square. And Fr is directly proportional to I1 minus I2 square. So during normal condition, the force is F naught is directly proportional to what? During normal condition, F naught is directly proportional to I1 minus I2 square. But now when the fault takes place, F naught is directly proportional to what? I1 plus I2 square. So the relay operates for the fault or not? Relay operates for the fault within the zone or not? Yes. So relay operates for the faults. Relay as F naught is greater than Fr, relay operates for fault within the zone. For fault within zone. In case of what? Interconnected system. For fault within the zone in case of interconnected system. Okay. Now this we have checked for what? This we have checked for interconnected system fault within the zone. No doubt we should also check for what? A radial system. We should also verify for a radial system whether the relay operates for the fault within the zone or not. Now let us consider radial system. Radial system means source will be only from one side. Radial system fault within the zone. Fault within the zone. Okay, within zone. Now, if you consider the radial system with the fault within the zone and check whether the relay operates or not. Check whether the relay operates or not. So, what will be the source here? There will be a source from only one side, source for only one side. Now let us observe by considering the fault, within the zone. Suppose if the short circuit fault takes place, within the zone, so due to the short circuit fault there will not be any CT2 current. Due to fault there will not be any CT2 current. Due to fault, CT2 current will not exist because the current circulates through what? Least impedance path. Through this short circuit path only the current will be circulated. I2 is what? 0. I2 is 0. So whenever the primary side current is 0, automatically the secondary side current is also 0. So what will be the relay coil current during during fault condition? Only I1. Due to fault, relay coil will carry only I1 current. Now what is the operating force during normal condition? F naught is directly proportional to N naught into I1 square, N naught into I1 square, and Fr is directly proportional to Nr by 2 into I1, Nr by 2 into I1 square, Nr by 2 into I1 square. Which will be more? So we will maintain N naught greater than Nr by 2. We will maintain N naught greater than Nr by 2. So operating force will be greater than the restraining force, and relay operates for fault. And relay operates for fault. Relay operates for fault. Within the zone or outside the zone? Within the zone. So this percentage differential relay is sensing the faults in case of interconnected system as well as radial system, and it is avoiding the faults which are taking place outside the zone due to dissimilar magnetization characteristics. Okay. Now let us go. I will analyze this once again. Observe here. Percentage biased relay or percentage differential relay. Percentage biased relay or percentage differential relay. So in case of percentage biased relay or percentage differential relay, what you will do, sir? We will connect the CTs on either side of the electrical equipment which is to be protected. This may be a transformer or alternator or bus bar, whatever it may be. We will compare the currents. We will compare the currents by connecting the CTs on either side of that electrical equipment. And in percentage biased relay, apart from the relay coil, we also have what? A restraining coil. Here we are having restraining coil. Additional restraining coil is connected. So here we are avoiding the operation of the relay to restrict for the fault outside the zone by using an additional restraining coil. Okay. So N naught is the number of turns on the relay coil, Nr is the number of turns on the restraining coil. Force is directly proportional to square of the MMF. N naught into I1 minus I2 square. Fr is Nr by 2 into I1 plus I2 square. So the relay will not operate. This is during what condition? Normal condition. The fault is outside the zone. The relay should not operate. Now let us consider the interconnected system and the fault within the zone. Interconnected system, fault within the zone. So what happens when the short circuit fault takes place? Here the current through the CT2 gets reversed due to fault. The current through the CT2 gets reversed due to fault. In case of what? Interconnected system. Interconnected system, the current through CT2 gets reversed. Okay. Now operating force gets I1 plus I2 square. Restraining force will be I1 minus I2 square. F naught will be greater than Fr, and the relay operates for the fault in case of what? Interconnected system. Now if you consider a radial system means source will be only from one side. Source will be only from one side. So there will not be any CT2 current. There will not be any CT2 current. So CT2 current is what? Zero. So what will be the current through relay coil during fault? I1 only. I1 is the current through the CT during fault. Okay. During fault, the relay coil current is what? I1 only. Okay. Then operating force is N naught I1 square, resistance force is NR by 2 into I1 square. We will maintain N naught greater than NR by 2. So for operating force greater than the restraining force. So the relay will operate during the fault within the zone. So this is how we have designed the percentage bias relay or percentage differential relay. Now let us analyze boundary condition. Boundary condition. So what is the operating force that you got? F naught is directly proportional to N naught into I1 minus I2 whole square, and Fr is directly proportional to NR by 2 into I1 plus NR by 2 into I2 whole square, NR by 2 into I2 square. This is the operating force and this is the restraining force. During what? Normal operation. This is during normal operation. There is no fault. So boundary condition means both the forces are equal. Operating force is same as restraining force. Now let us observe. So when operating force is same as restraining force, this square will get cancelled. You will get N naught into I1 minus I2, that is equal to NR by 2 into I1 plus I2. I1 plus I2. So from this, what is the relation for NR by N naught? NR by N naught ratio is what? NR by N naught. What do you get here? NR by N naught is I1 minus I2 by I1 plus I2 by I1 plus I2 by. So this ratio is known as bias of the relay. This is known as what? Bias of relay. This is known as bias of the relay. So difference of the currents to the average of the currents, we can say here. This NR by N naught ratio is nothing but slope of the relay. This is known as slope of the relay. Okay. So now that slope is provided by what? Restraining coil. So if you observe the variation of difference of the currents I1 minus I2, or we can also say that is nothing but relay coil current. Relay coil current, and average of the current I1 plus I2 by 2. This is nothing but current through the restraining coil. Current through the restraining coil. So here the curve appears like this. So this is in the form of y is equal to mx. Y is equal to mx. Here slope is what? NR by N naught. So the slope is introduced by restraining coil. Here the slope of this is NR by N naught. The slope is introduced by what? Restraining coil. So what will be the operating region? So this portion represents the operating region. Operating region. Okay. And this is the non-operating region. Non-operating region. Okay. So if the percentage bias relay is used, this portion is removed from operation. This portion is removed from operation. Okay, by inclusion of this restraining force. By inclusion of this restraining force. Okay. Now based on this we'll get different problems. This is very important. Very important. Based on this percentage slope that is provided, that is very important problems are there. We will discuss in further session. Okay, we will discuss in applications of this differential relay. So now we have discussed about percentage biased relay and percentage differential relay. Now let us go for the applications of this relay. Now let us discuss the applications of this percentage biased relay or percentage differential relay. So where do you use this percentage biased relay or percentage differential relay? They are used in protection of transformer, alternator and bus bar. Where do you use this relay, sir? Differential relay is used in protection of what? Transformer, alternator and bus bar. Now let us discuss about transformer protection. Transformer transformer protection. Let us analyze the transformer protection. Okay. So here the generation is three phase. Generation is three phase. So the transformer is also three phase. So the transformer primary consists of three-phase windings, and the secondary also consists of what? Three-phase windings. So we can make a point that as generation is three-phase, as generation is three-phase, transformer transformer is also three-phase transformer. Three-phase transformer is also three-phase. So primary side primary consists and secondary consists of three-phase windings. Secondary consists of three-phase windings. Okay. Primary consists of three-phase windings and secondary also consists of three-phase windings. Now, primary side there are three-phase windings, and secondary side also you have three-phase windings. Now we need to protect this transformer windings. Now we need to protect this transformer windings. So this is primary side and this is secondary side. So what are the faults that this primary and secondary of the transformer may experience? This primary and secondary of the transformer may experience which type of faults? My question is, primary and secondary of the transformer may experience which type of faults? Now let us observe here. Okay, the transformer windings may experience two types of faults. One is short circuit faults, short circuit faults, and the other one is interturn faults, interturn faults. So we need to protect the transformer winding from two types of faults. One is short circuit faults and the other one is interturn fault. What do you mean by interturn fault and what do you mean by short circuit fault? Now let us analyze. Interturn fault means, suppose if you consider the three-phase windings, suppose if you consider the three-phase windings, R phase, Y phase and B phase. So if you consider the three-phase windings, and if there is failure of insulation between the turns of the same phase winding, suppose some of the turns of R phase got failed, if there is a failure of insulation between the turns of the same phase winding, then it is treated as interturn fault. Interturn fault means what? Failure of insulation, failure of insulation, failure of insulation between the turns of same phase winding, same phase winding. Failure of insulation between the turns of the same phase winding is known as what? Interturn fault. Interturn fault. Failure of insulation between the turns of the same phase winding is known as interturn fault. What do you mean by short circuit fault? Short circuit fault means what? Short circuit fault means what? R phase, Y phase and B phase. So there are three phase windings, R phase, Y phase and B phase. So if the insulation gets failed between the phases, between the two phases, or between the phase and ground, between the phase or between the, if the failure of insulation between, if the failure of insulation takes place between the windings or between the windings and ground, that is said as short circuit faults. What are the different types of short circuit faults? This is nothing but line to line, line to ground, like that. So what are the different types of short circuit faults? Line to ground, line to line, double line to ground, triple line to ground faults. All these are what? Short circuit faults. Okay. Failure of insulation between the windings and between windings and ground, between windings and ground, that is known as what? Short circuit fault. So what do you mean by short circuit fault? Failure of insulation between the windings or between the windings and ground, that is treated as short circuit fault. Interturn fault means what? failure of insulation between the turns of the same phase winding, that is known as interturn fault. So here now we are analyzing the transformer protection. We are analyzing about transformer protection. So the transformer is to be protected against what? So a transformer is to be protected against what? So as generation is three-phase, transformer that is used is also a three-phase transformer. So the primary side consists of three-phase windings RYB. Suppose if you consider RYB, and the second side also consists of three-phase windings RY and B. Okay. So we need to protect this transformer windings. So what are the faults these windings may experience? It may experience either short circuit fault or interturn fault. Interturn fault means there will be turn to turn insulation also. If the failure of insulation between the turns of the same phase winding takes place, it is treated as what? Interturn fault. It is treated as interturn fault. What do you mean by short circuit fault? What do you mean by short circuit fault? Short circuit fault means what? Failure of insulation between the windings or between the windings and ground. Between the windings and ground. That is treated as short circuit fault. Suppose line to line, double line to ground, triple line and triple line to ground. All these are what? Short circuit faults. Now how do you give the short circuit fault protection and how do you give the interturn fault protection? Now let us see. Okay. If the rating of the transformer, if the rating of transformer, if the rating of the transformer is 1 MVA or 1 MVA or above 1 MVA, above 1 MVA, the short circuit fault protection is done by is done by percentage differential relay. Percentage differential relay. So what is your observation? If the rating of the transformer, is 1 MVA or above 1 MVA, 1 MVA or above 1 MVA, the short circuit fault protection is done by what? Percentage differential relay. So if the rating of the transformer is greater than or equal to 1 MVA, we will call this type of transformer as power transformer. It is known as what? Power transformer. So power transformer 1 MVA or above, it is known as power transformer. So the power transformer short circuit fault protection is done by what? Percentage differential relay. Very important, sir. Objective type question. So how the short circuit fault protection is done in case of power transformer? By using what? Percentage differential relay. Now let us come to the second fault. What is the second fault? Interturn fault. How this interturn fault are sensed? Interturn fault cannot be sensed by differential relay. Interturn fault is not sensed by differential relay. Okay, how do you sense the interturn fault? Interturn fault is sensed by Booker's relay. Interturn fault protection. Interturn fault protection is done by using Booker's relay. Booker's relay. So short circuit fault protection is done by percentage differential relay and interturn fault protection is done by using Booker's relay. Now let us see where this Booker's relay is located and how it will be operated. Where Booker's relay is located. Where Booker's relay is located. Where the Booker's relay will be located, sir? If you observe the transformer, where the Booker's relay will be located, it has the main tank and conservator tank. This is the main tank of the transformer. In main tank, what do you have? In main tank, we have the transformer core. There will be a transformer core. This is nothing but transformer core. And apart from this transformer core, there will be a transformer winding. There will be a transformer core and a transformer winding will be there. So this is the core of the transformer and this is nothing but winding of the transformer. This main tank of the transformer is completely filled with the transformer oil. This is completely filled with what? Transformer oil. There will be a transformer oil. This is nothing but transformer. Just wait. Hello. Sir, class the transformer oil. Okay. So now, apart from this main tank, the transformer, in case of apart from this main tank, the transformer also have conservator tank. So there will be a conservator tank also. So if you observe a power transformer, there will be main tank and conservator tank like this. Okay. So there will be conservator. So this is known as conservator tank. Conservator tank. So this conservator tank is also filled with transformer oil. It is also filled with transformer oil like this. Now where the Boccassile will be located? In main tank or conservator tank? Now observe here, Boccassile is located in between main tank and conservator tank. Boccassile is located where? In between main tank and conservator tank. This is the location of Boccassile. This is the location of Boccassile. So where it is located? It is located in between main tank and conservator tank. Okay. Use Boccassile is located in between main tank and conservator tank. Main tank and conservator tank. Conservator tank. So what does this Bocque's relay consist of? What does this Bocque's relay actually consist of, and how it will operate? So if you observe this Bocque's relay, it consists of two mercury floating switches. So there will be two mercury floating switches. This top switch is connected to alarm circuit and this bottom switch is connected to trip circuit. Bottom switch is connected to what? Trip circuit. So Bocque's relay consists of what? So if you observe the Bocque's relay, it consists of two mercury floating switches. Top switch is connected to alarm circuit and bottom switch is connected to trip circuit. Okay. Bocque's relay is connected in between main tank and conservator tank. Conservator tank. Bocque's relay is located in between main tank and is connected in between main tank and conservator tank. It consists of two mercury floating switches. Two mercury floating switches. Okay. The top switch is connected to alarm circuit and bottom switch is connected to trip circuit. Is connected to what? Connected to trip circuit. So top switch is connected to alarm circuit, bottom switch is connected to trip circuit. Where it is located in between main tank and conservator tank. Now I will share that Bocque's relay actual diagram how it will appear. Just wait, by seeing that you can get the clear idea. So if you observe, this is the Bocque's relay. So if you observe, this is a transformer. I think all of you are getting this screen, yes or no? Okay. So here it is a transformer. This is the main tank and this is the conservator tank. Bocque's relay is located where? So if you observe here, Bocque's relay is located in between main tank and conservator tank. This one, observe here. Bocque's relay is located in between main tank and conservator tank. Yes or no? It is located in between main tank and conservator tank. Okay. Now, what does this Bocque's relay actually consist of? If you observe, it consists of two mercury floating switches. This is mercury. This blue one is mercury. Okay. This one is mercury floating switches will be there. One switch is this top one is connected to what? Alarm circuit. Top switch is connected to alarm circuit. This bottom switch is connected to what? Trip circuit. Bottom switch is connected to trip circuit. Understood my point? So what happens actually the operation? What actually happens in this operation of this relay? Now let us observe. Okay. Now let us observe what happens actually in the Bocque's relay when interturn fault takes place. Now let us observe. Okay. Now, whenever this winding is experiencing any interturn fault, suppose this transformer winding is experiencing any interturn fault, what happens? Heavy current circulates in that path. Heavy current circulates in that path. Then this winding gets heated up. Yes or no? When interturn fault takes place, that heavy current will be circulated in that interturn fault, interturn path where the failure of insulation takes place, and the winding gets heated up, and the winding gets heated up. Once the winding gets heated up, once the winding gets heated up, the oil also gets heated up. This transformer oil also gets heated up. When transformer oil gets heated up, it decomposes to what? Gas. When transformer oil gets heated up, it decomposes to what? Gas. Understand my point? Thus, that gas should come out through this Buckel's relay like this. What is the path for gas? That gas should come out through this Buckel's relay like this. Okay, the path for gas should be through this Buckel's relay. Now, what happens? Observe when that gas is coming out through this Buckel's relay. What about this situation in the Buckel's relay? Now, let us observe here. This floating switch will change its orientation. Floating switch will change its orientation. Okay. Normal condition, this mercury is not conducting between these 2 points. But whenever the floating switch gets, whenever the gas exerts a pressure on this flap, what happens? It will change its orientation, and the mercury will conduct between these 2 points and initiates the alarm signal and trip signal. Okay. Now I will give the explanation regarding that in our slide. So here, so this Buckel's relay consists of what? So there will be, so one side it is connected to what? One side it is connected to main tank, and the other side it is connected to um, conservator tank. This Buckel's relay is also filled with what? Transformer oil. So there will be two mercury floating switches. There will be two mercury floating switches. This top switch is connected to alarm circuit. Here it is connected to what? Alarm circuit. Alarm circuit. And this bottom switch is connected to trip circuit. Bottom switch is connected to trip circuit. Okay. So this is mercury, and this is the other mercury. During normal condition, the mercury switch will be in this orientation. This will not conduct between these 2 points. So this is off state. This is off state. But whenever the transformer oil gets heated up and decomposed to gas, that will be coming out through this Buckel's relay. Then the mercury floating switch will change its orientation from this point to this point like this. So it will, the mercury will conduct between these 2 points, and it will result in what? On state, and it is result in on state. During normal condition, mercury will not conduct between the 2 points, but whenever the interturn fault takes place, what happens? The transformer winding gets heated up and it decomposes the oil to gas. That gas should come out through this Buckel's relay, and it will result in operation of the relay. Okay. So I will be giving the points what actually it will happen. Observe here. When interturn fault takes place, when interturn fault takes place, transformer winding gets heated up. Transformer winding gets heated up, and transformer oil gets heated up, and decomposed gas, and decomposed to gas. When interturn fault takes place, what happens? Transformer winding gets heated up, transformer oil also gets heated up, and it is decomposed to gas. When it is decomposed to gas, the gas should come out through this Buckel's relay. Gas should come out through this, come out through this, through Buckel's relay. come out through the Bockel's relay. Then the mercury floating switches will change its orientation. Then the mercury floating switches changes its orientation. Mercury floating switches will change its orientation and and results in operation of relay. Operation of relay. Okay. So this Bocas relay is a gas activated relay. It is a gas activated relay. Okay. It is a gas activated relay. Now the question generally comes, Bocas relay will sense only interturn fault or short circuit fault or both. Bocas relay will sense only interturn fault or only short circuit fault or both. It can sense both. The question is, Bocas relay can sense only interturn fault or short circuit fault or both. So it is a gas activated relay. When short circuit fault also takes place, then also heavy current will circulate in that winding. Short circuit fault also will result in heavy current circulation in that winding. Then also oil gets heated up, the winding gets heated up. Then also the oil gets heated up and it is decomposed to gas. So the Bocas relay will sense both the interturn fault as well as short circuit fault. Bocas relay will sense both interturn fault as well as short circuit fault. But why the why the short circuit fault protection is done by percentage differential relay? Why the short circuit fault protection is done by percentage differential relay? My question is, why you are using percentage differential relay here? Again, the answer is like this: the time of operation of Bocas relay will be more. The time of operation of Bocas relay will be more. So here what happens, the winding should heat it up, oil should heat it up and decompose to gas, then the relay will operate. So time of operation of Bocas relay will be more. If you allow short circuit current, for such high time, the winding may get damaged. So that is a disadvantage. Here. Okay. That's why the short circuit fault protection is done by what? Percentage differential relay. Okay. Now the analysis is like this. Bocas relay can sense both. It can sense both short circuit fault and interturn fault. Interturn fault. Bocas relay can sense both short circuit fault and interturn fault. Okay, but short circuit fault protection. But short circuit fault protection. Is done by percentage differential relay. Percentage differential relay. Okay. Bocas relay can sense both short circuit fault and interturn fault, but the short circuit fault protection is done by what? Percentage differential relay. Why? Because time of operation of Bocas relay will be more. If short circuit fault is allowed for such high time, winding may get damaged. Winding may get damaged. Okay. So if short circuit fault is allowed for such high time, winding may get damaged. No doubt. Objective type question may be asked like this: Bocas relay can sense short circuit fault, interturn fault, both. Answer is both. It can sense both short circuit fault as well as interturn fault. But the short circuit fault protection is done by percentage differential relay. Why the additional relay is used? because this Bockel's relay takes more time of operation. If short circuit fault is allowed for such a high time, what happens? The winding may get damaged. Okay. So this is about Bockel's relay. Now let us go for short circuit fault protection in case of transformer winding. Okay. Short circuit fault protection of transformer winding. Transformer winding. Short circuit fault protection of transformer winding. Okay. So here transformer is three phase or single phase. Transformer is three phase or single phase. Generation is three phase. So the transformer that is used is also a three phase transformer. Generation is three phase. So the transformer that is used is also a three phase transformer. Okay. Generation is three phase. Generation is three phase. So transformer used. So transformer used is is also a three-phase transformer. Three-phase transformer. Generation is three-phase. So transformer used is also a three-phase transformer. So whenever you are saying three-phase transformer means the primary consists of how many windings? Three-phase windings. And secondary also consists of how many windings? Three-phase windings. Okay. So primary consists of three-phase windings, and secondary consists of three-phase windings. So there will be primary side and secondary side. Now whenever there are three-phase windings, you can connect in two different configurations. So primary can be connected either in star or delta. Can be connected either in star or delta. Secondary also can be connected either in star or delta. Okay. So as there are three-phase windings on primary side and secondary side, they can be connected either in star or delta. Okay. So as there are three-phase windings, they can be connected. They can be connected, yeah, in star or delta. They can be connected either in star or delta. Okay. So primary can be connected either in star or delta. Secondary also can be connected either in star or delta. So based on that, what are the different types of power transformer? PTR means what? Power transformer. What are the different types of power transformers that are available here? So what are the different types of power transformers that are available here? Power transformer primary can be connected in star, secondary also can be connected in star. Primary can be connected in star, secondary also can be connected in star. Primary can be connected in delta, secondary also can be connected in delta. Primary can be connected in delta, secondary can be connected in star. Primary can be connected in star, secondary can be connected in delta. So these are the different types of power transformer configurations. Okay. So what are the different types of power transformer configurations? Star star, delta delta, delta star, and star delta transformer. Now, what is the phase shift that you will get in different types of configurations? So, what is the phase shift? What is the phase shift that you will get from primary side to secondary side? Now, observe, this is very important, sir. What is the phase shift that you will get from primary side to secondary side in case of this four different configurations that you need to analyze here? So, in case of star star, you will get either 0 degrees phase shift or 180 degrees phase shift. In case of star star, what do you get? In case of star star transformer, you can get either 0 degrees phase shift or 180 degrees phase shift. In case of star star transformer, you can get either 0 degrees phase shift or 180 degrees phase shift. In delta delta also, you will get either 0 degrees phase shift or 180 degrees phase shift. This you will be studying in transformer, sir. This you will be studying in transformer. Okay. And in case of delta star, between primary side current and secondary side current, you may get plus or minus 30 degrees and 180 plus or minus 30 degrees. Okay, you may get how much phase shift? Plus or minus 30 degrees, 180 plus or minus 30 degrees. Okay, in case of delta star, you may get four different phase shifts: plus 30, minus 30, 180 plus 30, and 180 minus 30. Okay, in case of star delta also plus or minus 30 degrees and 180 plus or minus 30 degrees. So what is your observation here? In case of delta star and star delta transformer, there is a definite phase shift of how much? 30 degrees. There is a definite phase shift of 30 degrees between primary side and secondary side. Understood my point? In case of delta star and star delta transformer, there is a definite phase shift of how much? 30 degrees from primary side to secondary side. Okay. Now, what are the basic requirements? Now coming to the how can we implement the short circuit fault protection by using percentage differential relay. The short circuit fault protection is implemented by using what? A percentage differential relay. So for implementing the differential protection, what are the basic requirements? In the last class I have said, what are the basic requirements? You require at least two similar quantities. Two similar electrical quantities are required. Two similar electrical quantities are required. So here, what are the two similar electrical quantities? You will get one primary side current and a secondary side current. One is primary side current and the other one is secondary side current. So we will compare primary side current and secondary side current. The first requirement is satisfied. We got two currents. We got two currents to compare. Now coming to the second requirement. What is the second requirement? These two currents must be out of phase by how much? 180 degrees. This primary side current and secondary side current must be out of phase by how much? 180 degrees. But if you observe this delta star and star delta transformer, there is a definite phase shift of how much? 30 degrees. There is a definite phase shift of 30 degrees. Understood my point? In case of delta star and star delta transformer, there is a definite phase shift of 30 degrees. So, but what is the required phase shift here? The required phase shift is 180 degrees. But here, how much phase shift is there? 30 degrees phase shift is there. How do you convert this 30 degrees phase shift to 180 degrees phase shift? How can we convert this 30 degrees phase shift to 180 degrees phase shift? Here we need to use what? A condition. What is the condition that must be satisfied here? To cancel out this 30 degrees phase shift, the CT configuration that you are connecting on primary side and secondary side should be opposite to that of PTR configuration. To cancel out the 30 degrees phase shift, how the CTs must be connected? Opposite to that of PTR configuration. That means if PTR is delta, CT must be connected in what? Star. If PTR is star, CT must be connected in delta. Okay. And if PTR is star, CT must be connected in delta. If PTR is delta, you need to connect CT in star. So PTR configuration and CT configuration should be opposite. So star star means here you should connect between what? Delta delta. And delta delta means star star. Okay. So what is your observation here? What point you can make in case of delta star and star delta transformer, there is a definite phase shift of 30 degrees. There is a definite phase shift of how much? 30 degrees from primary side to secondary side. So in case of delta star and star delta transformer, there is a definite phase shift of 30 degrees from primary side to secondary side current. But required phase shift is how much? 180 degrees. But the required phase shift is 180 degrees. To cancel out this phase shift, what do you need to do? We need to connect the CTs in opposite configuration to that of PTR configuration. Okay. To nullify this 30 degrees phase shift, the CTs are to be connected in opposite configuration to that of PTR configuration. To nullify the 30 degrees phase shift, the CTs have to be connected in opposite configuration to that of PTR configuration. This is very important, sir. This table has to be kept in mind. Table is nothing but if PTR is delta star given, CTs must be oppositely connected, star delta. Okay, PTR configuration and CT configurations are opposite. That you need to keep it in mind. Okay, because CT ratio calculation is very important. I will solve the problems now. Now that is very important. Okay, now I will show with an example here. Now I will show with an example. Suppose if the transformer is delta star, sorry, if the transformer is delta star, it is given like this. So this is primary side winding and secondary side winding. This is primary side and secondary side winding. Okay. Here, suppose if you consider delta star transformer, primary side is delta, secondary side is what? Star connected. Primary side is delta, secondary side is star connected like this. This is secondary side star connected. Primary side is delta. This is delta connection. Okay. So this is how a PDR is connected. Now observe. Now we need to protect this power transformer. This is the power transformer given by the company. Now we need to implement the protection to this power transformer. Now we need to design the protection system for this power transformer. So how do you design the protection system for this power transformer? Now let us observe here. So what you will do, we will connect the CTs on, just wait, just wait, sir. So now we need to protect this transformer. Now we need to protect this transformer. So how do you protect this transformer? Any idea? Any idea how to protect this transformer? Just wait. I need to arrange this. So okay, right now my aim is to protect this transformer by using percentage differential relay. How can we protect? So we are comparing the primary side current with secondary side current. So for that, what do you do? We will connect the primary side CT. Primary side we will connect the CTs. So the primary side CTs. There are three CTs for each phase. Primary side you have three CTs. The primary of the CT will be directly connected in series with the line. So here these are secondary side CTs. Okay. So CT also has primary and secondary. CT also has primary and secondary. Primary of the CT will be directly connected in series with the line, but secondary of the CTs connection is based on the configuration of the PTR. Now observe here, if the PTR is delta star, PTR is delta star, CTs must be connected in star and delta. CTs must be connected in star and delta. So now observe here, primary is delta. So CTs must be connected in what configuration? Star configuration. Now observe here, CT secondaries must be connected in what configuration? Star configuration. So here you have three outputs. Here you have three outputs. So this is primary side outputs. Okay. On secondary side, if you observe, primary is star, CTs must be connected in delta. Now CT secondaries are connected in what configuration? Delta configuration like this. CT secondaries are connected in delta configuration. Here the delta also you will get three outputs. Here delta also you will be getting the three outputs. Delta also you will be getting the three outputs like this. Now observe here, this is delta outputs. Now we need to compare this primary side current with what? Secondary side current. So this first point is to be connected to this first point, second point is to be connected here, and the third point is to be connected here. So this is how the CT configurations are to be done. The primary is directly the line current of the transformer. The connection delta or star is based on the secondary side. Primary is delta, PTR primary is delta. So CTs must be connected in star. Secondary is star, CTs must be connected in delta. And here, where do you connect the relay coil? Relay coil is connected exactly at the middle. So at the middle of that, we will connect the relay coil. Here we will connect. Sorry, where do you connect the relay coils? This relay coil is connected exactly at the middle. So this is how a delta star transformer is to be observed. Okay. Now I will repeat this short circuit fault protection of transformer winding. So how do you protect the short circuit fault protection? By using what? Percentage differential relay. Percentage differential relay will be using. Here what we will compare? Here we will compare primary side current with secondary side current. Primary side current with secondary side current. Primary side current with secondary current. Okay. Secondary current. Primary side current with secondary side current. Okay. So generation is three phase. Transformer that is used is also three phase transformer. So primary or secondary can be connected either in star or delta. So based on that, there are four configurations that you'll get: star star, delta delta, delta star, star delta. Okay. So in case of star star and delta delta, 0 degrees, 180 degrees phase shift you get. But in case of delta star and the star delta transformer, you'll get a definite phase shift of how much? Plus or minus 30 degrees. 30 degrees phase shift you'll get. But required phase shift is what? 180 degrees. Required phase shift is 180 degrees. To cancel out that 30 degrees phase shift, what you will do? To nullify 30 degrees phase shift, CT configuration should be oppositely connected to that of PTR configuration. CT configuration should be opposite to that of PTR configuration. If the PTR is star, CT must be delta. If PTR is delta, CT must be star connected. Understood my point? So that's what I have showed here. Here I have showed for a delta star PTR, delta star power transformer. Primary side is delta, secondary side is star. So CT secondaries must be connected in star and delta. Okay. So this is very useful because for relay CT ratio calculation, very frequently asked in examination, this data is required. So if you solve one or two problems, you'll be getting the idea. Okay. So the question is given like this. The question is given like this. A power transformer rated 132 by 11 kV, sorry, 132 by 33 kV, 132 by 33 kV, delta star connected, delta star connected is protected by differential relay, differential relay using CT ratio on HT side as 400 by 5. CT ratio on HT side is what? 400 by 5. Calculate a CT ratio on LT side. Calculate CT ratio on LT side. Okay. So what is asking? Observe this question clearly. Observe this question clearly. What he has given: a power transformer rated 132 by 33 kV. A power transformer is rated 132 by 33 kV. Delta star connected is protected by a percentage differential relay or a differential relay. Percentage differential relay or a differential relay. Using a CT ratio of HT side on 400 by 5. Calculate the CT ratio on LT side. So whenever you observe such problems, calculation of CT ratio, first what you need to do, first you need to identify what is the data given in the question. First what you need to do, what is the data given? What is the data given, sir? He is saying that power transformer rated 132 by 33 kV is to be protected. What is the connection? Delta star connection. This is to be protected by a differential relay. So whenever you are saying a differential relay, what you need to do? We will connect the CTs on either side. Here we will connect the CT on HT side and CT on LT side, CT on HT side will be connected, as well as CT on LT side will be also connected. So what is the CT ratio on HT side given? CT ratio on HT side given as what? 400 by 5. CT ratio on HT side given as 400 by 5. What you need to calculate? CT ratio on LT side, that you need to calculate. Let it be capital IX by small ix. Let it be capital X by small ix is to be calculated. Okay. This is the data that is given in the question. First, you need to identify what data is given in the question. Then, so this is the given data. What is your observation? If power transformer is delta star, power transformer is delta star. CT must be connected in what? Star delta, opposite. So here it is primary side is delta. So here you should connect with star. Okay. And here secondary side it is star. So here you should connect with what? Delta. Okay. CT configuration should be opposite to that of PTR configuration. And the star point is to be connected to this delta point. Star point is to be connected to this delta point, and the relay coil should be placed exactly at the middle, and the relay coil is to be placed exactly at the middle. So this is the given solution. Now observe here. During normal condition, the solution for this can be obtained like this. During normal condition, relay should not carry any current. During normal condition, relay should operate or it should not operate? Relay should not operate. So relay current should be how much? 0 amperes. First that you need to identify. Okay. Now what is the given data here? 400 by 5 given. That means if this is 400 amperes, what will be the current on secondary side? 5 amperes. If primary side is 400 amperes, current on secondary side is how much? 5 amperes. That you need to identify. So in case of star connection, phase current and line current will be same. So if this is 5 amperes, here it will be how much? 5 amperes. So at this point, relay current is 0 amperes. This is 5 amperes. So what will be the current here? It is also 5 amperes. Okay, understood my point. It is also 5 amperes. Now here you need to calculate this capital Ix value as well as what? Small ix. Capital X and small ix value you need to identify. So in case of delta connection, so for delta, I phase is what? I phase is IL by root 3. IL by root 3. So this is for delta connection. Okay. For delta, I phase is IL by root 3. So here line current is 5 amperes. What will be the phase current? Small ix can be calculated. That is how much? 5 by root 3. So you got one value. Small ix value you got. That is how much? 5 by root 3. But here capital Ix is to be calculated. How do you calculate capital Ix, sir? How do you calculate capital Ix value? Any idea? So transformer is a constant power device or a variable power device? Transformer is a constant power device or variable power device? Transformer is a constant power device. Okay. So for calculation of capital X, small x completed, capital X we need to calculate. We should use transformer is a constant power device concept. Okay. So primary side, what is the power rating? Root 3 times of V1 I1. Secondary side is also root 3 times of V2 into I2. So root 3 gets cancelled. V1 is how much? 132. I1 is 400. 132 into 400 is equal to, this root 3 gets cancelled out. No, V2 is how much? V2 is how much? 33. 33 into capital Ix. So how much do you get here? Capital Ix is 400 into 132 by 33. 11 3s are 33. 11 1s are 11 2s are 3 1s are, so no, 11 3s are 11 1s are, okay, right. 3 4s are 4 4s are 1600 amperes. Now, what is the CT ratio? CT ratio on LT side. CT ratio on LT side is what? Capital Ix by small ix. So what do you get here? 1600 by 5 by root 3. 1600 by 5 by root 3. So what is your answer? 1600 root 3 by 5 is the answer. 1600 root 3 by 5 is the answer. Okay. So what is your observation here? A PTR rated 132 by 33 kV delta star connected is protected by a percentage differential relay using the CT on HT side with ratio 400 by 5. HT means high tension side. HT side means what? High tension side. What is asking to calculate? What is the CT ratio on LT side? He is asking to calculate what is the CT ratio on LT side. So how do we let the CT ratio on LT side be how much? Capital X by small x. So what is the data given? It is delta star. Primary transformer is delta star. Power transformer is delta star. So here PTR is delta star means the CT should be oppositely configured. CT should be connected in star and delta. The star point is to be connected to this delta point. Star point is to be connected to this delta point, and the relay coil should be connected in the middle. What should be the current through the relay coil during normal condition? During normal condition, relay should not carry any current. So 0 amperes should be relay coil current. So 400 by 5 again, this is 400 means this is 5 amperes. So here you get small ix is 5 by root 3. For calculating capital X, what do you need to do? Transformer is a constant power device. So equal powers on primary side and secondary side. Okay. You get the CT ratio on LT side. LT side means low tension side. Now I will give one problem. If you try to solve, okay, you try to solve on your own. I will give one problem. A power transformer rated 33 by 11 kV, star delta connected, is protected by circulating current protection scheme. Power transformer rated 33 by 11 kV delta star connected is protected by circulating current protection scheme. Circulating current protection scheme is also nothing but a differential relay only. Okay, using CT ratio on LT side as 200 by 1. CT ratio on LT side is 200 by 1. Calculate CT ratio on HT side. Calculate CT ratio on HT side. Now I'll give you time 5 minutes time and try to solve this. So based on the same analysis, here power transformer rated 33 by 11 kV delta star connected is protected by circulating current protection scheme. Circulating current protection or differential relay, both are same. Okay. Using CT ratio on empty side is 200 by 1. Calculate the CT ratio on HT side. Try to solve this, sir. First, identify what data is given. First, identify what data is given in the question. Okay. What is the data given in the question? First, identify. And try to solve it. Okay. And try to solve it. So, any answers came? No, it is answer. I will try to solve this. Just if you have got just if you have any doubt. Okay. So first observe what is the data given. So what is the data given? He has given a power transformer. What is the star delta connected? 33 by 11 kV. 33 by 11 kV. And whenever you are saying differential elements, what you will do? We will connect the CTs on both sides. We will connect the CTs on both sides. So this is the CT on LT side and CT on HT side. Okay. So now here what he has given CT ratio on LT side given. LT side CT ratio given as what? 200 by 1. He is asking CT on HT side. Let it be some capital X by small x. Capital X by small x. Now here power transformer is star delta, means it should be opposite configured, delta and star. Okay, delta and star. Now this delta point is to be connected to the star point, and here relay coil should be connected in the middle. What should be the current through the relay during normal condition? 0 amperes. Here CT ratio on HT side is asking calculate, LT side it is 200. That means if here you are flowing 200 amperes, what will be the current here? 1 ampere. If current here on the primary side is 200 means second side will be 1 ampere. 200 by 1. Okay. So here also the current will be 1 ampere. Here what will be the current? This is 0 amperes. Here it is 1 ampere means here also it is 1 ampere. Now we need to calculate this small ix. We know capital Ix. We know line current. We require phase current. So in case of delta, I phase is what? IL by root 3. IL by root 3. So here Ix is 1 by root 3. Ix is 1 by root 3. So we got capital I, small ix value. How do you calculate capital X? For calculation of capital X, use transformer is a constant power device. Power device. Transformer is a constant power device. So root 3 times of V1 I1 is equal to root 3 times of V2 I2. So what is V1 here? 33. I1 is Ix. 33 into Ix must be equal to root 3 will get cancelled. What is V2 now? V2 is 11 into 200. 11 into 200. So 11 3 is. So Ix is what? 200 by 3. 200 by 3. Now what is the CT ratio? What is the CT ratio on LT side? LT side CT ratio is what? Capital Ix by small ix. That is 200 by 3 by what is small x? What is small x? 1 by root 3. So that is 200 into root 3 by 3. 200 into root 3 by 3. So you can write it as 200 by root 3 also. 200 by because root 3 square, root 3 will get cancelled. Answer is 200 by root 3. So this is the CT ratio calculation. Understood my point? Okay. Now I will try to share one problem given in your CRO, classroom object user. I will try to share that. Just be patient. I will try to open that. Now observe, I'm sharing that screen. Now observe problem number 4, sir. Problem number 4, try to answer. Now I request the students to try to solve problem number 4. Try to solve problem number 4. A 3-phase 11 by 66 kV delta star transformer. 3-phase 11 by 66 delta star transformer. A 3-phase 11 by 66 delta star transformer is protected by MERS price scheme as CT ratio of 400 by 5 on LT side. Calculate CT ratio on HT side. Try to solve this. Problem number 4. Try to solve problem number 4, sir. First observe what is the given data. 3-phase transformer given 11 by 66 delta star. MERS price protection is also nothing but MERS price scheme is also nothing but a differential relay. This MERS price scheme is nothing but differential relay on. Differential relay or circulating protection relay or MERS price differential relay are same. Okay. So what is the data given here? This is the differential relay only. Okay. Now has a CT ratio of 400 by 5. What is asking to calculate? CT ratio on LT side he is asking to calculate. HT side delta star is protected. CT ratio on LT side given as 400 by 5. What is the CT ratio on HT side? Try to calculate. I am resharing my whiteboard. Problem number 4. Okay. I will try to solve that. So here problem number 4 in CRO. What is given? A power transformer given. A power transformer given. What is the rating of that power transformer given? 11 by 66 given. 11 by 66 kV delta star transformer is given. So we are protecting a differential relay means we will connect the CTs on both sides. Here the CT on LT side, CT on HT side. What is the given data? CT on LT side is 400 by 5. CT on LT side given as what? 400 by 5. What is the CT ratio on HT side? Capital X by small x. Yeah, that you need to calculate. So now how do you calculate? How do you calculate? Try to solve this. So whenever such type of problem is given, first what you need to do? First what you need to do here, you observe what is the given data. Then here power transformer is delta star. Power transformer is delta star. So CTs must be connected in what configuration? CT configuration is to be opposite to that of what? Power transformer configuration. So CT must be connected in star and delta. CTs must be connected in star and delta. Okay. So this star point is to be connected to this delta point, and in the middle you should connect what? Relay coil. And in the middle you should connect the relay coil. Yeah. Relay coil is to be connected in the middle. Okay. So here this relay coil should not carry any current during normal condition. Current to the relay should be how much? 0 amperes. So it is given 400 by 5 means if this is 400 amperes, what is the current here? 5 amperes. So this is also 5 amperes. So here also you call 5 amperes. So here you need to calculate this capital X and small ix. So what is the value of small ix? 5 by root 3. Ix is 5 by root 3. What about primary capital X? For capital X, what do you need to do? Transformer is a constant power device. Root 3 times of V1 I1 is equal to root 3 times of V2 I2. V1 is how much here? 11 into I1 is 400. V2 is how much? 66. I2 is what? Ix. So here Ix, capital X value is what? 400 by 6. 400 by 6. So here you need to calculate the CT ratio on HT side. So what is the CT ratio on HT side? That you will get capital X by small ix. Capital X by small x. Capital X is what? 400 by 6 by 5 by root 3. If you simplify this, you will get 23. So you can write it as 23 by 1, or you can also write it as 23 is to 1. 23 is to 1. 23 by 1 or 23 is to 1. Understood my point here? 23 by 1 or 23 is to 1. Okay. So understood what is the given data here? Power transformer rated 11 by 66 kV, delta star transformer given. CT ratio on LT side given as 400 by 5. Is asking to calculate the CT ratio on HT side. So now CT ratio on HT side will be what? CT ratio on HT side will be what? How do you calculate? CT configuration should be opposite to that of PTR configuration. So based on that, you should calculate. So answer is what? 23 is to 1. So actually you get 23 if you simplify that. You can write it as 23 by 1 or 23 is to 1. Okay. Now if you observe the options that are given in that question, so if you observe this problem number 4, 23 is to 1. Option B is the right answer. Got my point? Merz price differential relay or circulating current protection scheme all are same. Okay. Now let us go for one more problem based on this. One more problem model is there. If the question is given like this, a power transformer rated 10 MVA, 132 by 33 kV, delta star connected. A power transformer rated 10 MVA, 132 by 33 kV, delta star connected, is protected by percentage differential relay. Percentage differential relay. Calculate CT ratios on both sides. If so, the condition is given like this: if a current of 5 amperes is 5 amperes is to be circulated in pilot wires. Now observe, a power transformer rated 10 MVA, 132 by 33 kV, delta star connected, is protected by percentage differential relay. Calculate the CT ratios on both sides if the current of 5 amperes is to be circulated in pilot wires. Okay. Now how do you find the solution for this problem? Now what is the problem given, sir? Here power transformer rated how much? 10 MVA given, 132 by 33 kV given, delta star connected. So this is protected by a percentage differential relay. So we will connect the CT ratio on HT side. We need to calculate, and the CT ratio on LT side also to be calculated. Let it be some capital X by small x. This is capital Iy by small iy. Okay. Here PTR is delta star. PTR is of what configuration? PTR is delta star. So CT configuration should be opposite to that of PTR configuration. If it is delta means here you should connect star. If it is star means here you should connect delta. Okay. So this star point is to be connected to this delta point, and the relay should be connected where? And the relay coil should be connected in the middle. This relay coil should not carry any current. So relay should carry what current during normal condition? 0 amperes should be carried by the relay. Okay. Now here you need to calculate this capital Ix and small ix. Here you need to calculate this capital Iy and small iy. What is the given data? These CT secondaries are connected by means of what? Pilot wires. We know that CT secondaries are connected by means of pilot wires. How much current is to be circulated in pilot wires? Given 5 amperes. That means here the current that is to be circulated in pilot wires is how much? 5 amperes. 5 amperes is to be continuously circulated in pilot wires. From this, what is the value of small ix? Directly you can write it as what? 5 amperes. What is the value of small iy? So iy is phase current. This is 5 amperes is line current. 5 by root 2. So small ix and small iy completed. How do you calculate capital Ix and capital Iy? So S is root 3 times of VL IL. So from that we require Ix value. Ix is S by root 3 times of VL. So S is how much here? 10 MVA. 10 into 10 power 6 by root 3 into VL. VL is how much? 132 into 10 power 3. So this is capital X. What about capital IY? This is also constant power device. S by root 3 VL. S is how much? 10 into 10 power 6 by root 3 into VL is how much here? 33 kV. 33 into 10 power 3. So you got capital Ix and capital Iy, small ix and small iy. Okay. So all the values are computed. From this we can calculate what? The CT ratios. Okay. I think all of you got the idea regarding this. Okay, how to calculate the CT ratios. How to calculate the CT ratios. You got the idea or not? Yes or no? Okay. Now let us take one more model. Generally you will be confusing here. Suppose the problem is given like this. A power transformer rated a power transformer rated suppose uh, 66 or rated 33 by 11 kV, 33 by 11 kV, delta star connected, delta star connected. CT ratio on LT side, CT ratio on LT side is 500 by 5, 500 by 5. Calculate CT ratio on HT side, CT ratio on HT side. Now try to solve this. A power transformer rated is 33 by 11 kV. Delta star connected. CT ratio on LT side is 500 by 5. Calculate CT ratio on HT side. So how do you calculate? Observe this problem carefully. Observe this problem carefully. So here, what is the given data? Let us observe. So here, power transformer given 33 by 11 kV given. Delta star connected here. So now for implementing the differential protection, what you will do? You will connect the CTs on HT side and CTs on LT side. CT on LT side given as 500 by 5. Now here the power transformer configuration should be opposite to that of PTR configuration. PTR is delta star means this should be star and this should be delta. The star point is to be connected to this delta point, and the relay coil should be connected in the middle. So this relay should not carry any current during normal operation. Okay. Now observe here. CT ratio on LT side is what? 500 by 5. So here, if 500 amperes of current is flowing, here you should take the phase current, sir. This 5 amperes is, listen this carefully. Here, this 5 amperes is to be taken on phase value, not the line current. If you take the line current, it will be wrong. So this 5 amperes is phase current. Now here, what will be the line current? 5 root 3. 5 root 3 is the line current. Okay. Now here, what will be the current? 5 root 3. Now you need to calculate this capital Ix and small ix. So here, what will be the value of small ix? Small ix is 5 root 3. So for calculation of capital X, transformer is constant power device. Root 3 V1 I1 is equal to root 3 times of V2 I2. Root 3 gets cancelled. V1 is how much? 33 into Ix is equal to 11. Sorry, Ix is equal to 11 into I2 is how much? 500. So capital Ix is what? 500 by 3. 500 by 3. Now what is the CT ratio on HT side? Here the solution for this what? CT ratio on HT side is CT ratio on HT side is capital X by small x. Capital X by small x. Capital X is what? 500 by 3. Capital X is 500 by 3. Small x is what? 5 root 3 by 5 root 3 is the answer. Okay. Understood my point? So this is how you need to calculate the CT ratios. This is how you need to calculate the CT ratios. Okay. Now I will stop here. I will take the doubt session. I will take the doubt session. So I will lower all your hands. If anyone has the doubts, you can raise the hand, sir. If anyone has the doubt, you can raise the hand. If you are having doubts, you can raise the hand. Okay. G Nagasai,
Hello.
ask your doubt.
Good evening, sir.
Hmm.
Sir, how we can say the CT ratio if the question is given delta star, we have to say star delta.
Well, you are asking how the CTs are to be configured. Huh?
Yes, sir. Yes, sir.
So I have already explained now here while explaining the power transformer protection. This way. Here I have given no. If you observe in case of delta star and star delta transformer, there is a definite phase shift of how much? 30 degrees. Okay. This
Yes,
30
sir.
degrees, we require 180 degrees phase shift. We require how much phase shift? 180 degrees.
180 degrees.
This 30 degrees phase shift is to be nullified. For that, what do you need to do? We need to connect the CTs in opposite configuration to that of PTR configuration. Okay. So why
Okay.
how that will be cancelled means now if you observe in case of delta star, I will give the logic here. Just observe. So suppose if you take a delta star power transformer, delta, this is delta, and this is star, this is delta star. Okay. So here, suppose this is IR, this is IY, and this is IB. What will be the current here? Nagasai, what will be the current at this node?
I line current
What will be the
root
current?
root 3 times of I phase.
Not rule 3 times. If you apply KCL at this node, what will you get? In terms of IR and IB, what will be the current? What will be the current? If you apply KCL at this node, what do you get? IR minus IB, yes or no?
Yes, sir. Yes, sir.
Okay. So this is IR, this is IY, and this is IB. So here on primary side, what are you getting? IR minus IB. So this is minus IB. Okay. So this is the current that you are sensing. So this is IR minus IB. Okay, understood my point? So this
Yes,
is
sir.
how much? 30 degrees phase. On the other side, what you are getting here? IR, IY and IB. IR, IY and IB. Okay. So if you directly compare by connecting the CTs, here if you are connecting the CT on primary side and secondary side, suppose if you compare CT1 and CT2, there will be out, these currents will be out of phase by how much? 30 degrees, yes or no?
Yes, sir.
Understood my point? That's why what
Yes,
you
sir.
are doing, that's why what you are doing here, these secondary side CTs and primary side CTs, the CTs must be oppositely configured. The CTs must be oppositely configured. So if you oppositely configured, here the PTR is star connected, yes or no? Here the PTR is star connected. So whenever the PTR is star connected, CTs must be in what configuration? Delta configuration, yes or no? Understood my point?
Yes. Yes, sir.
PTR PTR star. Now here uh, we are comparing this current. Now observe here. We are comparing this current. So what will be the current here now? What will be the current here? So this is IR, okay, and here it is IB. Understood my point?
Yes, sir.
So what will be the current here? IR minus IB.
IR minus IB.
IR minus IB. Now you can compare IR minus IB with IR minus IB, but you can't compare IR with IR minus IB. Understood my point?
Yes, sir.
Got my point?
Yes, sir.
So that's why we are connecting CTs in opposite configuration to that of PTR configuration. Got the idea?
Yes, sir. Yes.
Okay.
Okay.
Sagar. Sagar,
Hello, sir.
ask your doubt.
Sir, in Buckholes relay, what is the purpose of alarm circuit and trip circuit, sir?
Trip circuit will initiate the action of circuit breaker. Okay. The
Okay, sir.
circuit breaker will disconnect the transformer from healthy section. Okay. Whenever there is a fault, the transformer is to be disconnected from the live circuit. No. That is done by what? Trip circuit. Okay. The trip signal will issue to the circuit breaker and the circuit breaker will get tripped. Understood my point? Alarm signal will be initiated because it is a fault inside the transformer. No. Transformer is the heart of this power system network. Yes or no? So to sense that fault is taking place inside the transformer, alarm will be initiated.
Fault means in a transformer, which type of fault, sir?
I have said no, the winding may experience two types of faults, internal faults and external faults. Interturn faults and short circuit faults. Sir.
Thank you, sir.
Abjit,
Good evening, sir.
good evening.
Sir, in power transformer with delta, delta and star, star, why we are necessary to take opposite configuration in CT
Power
connection?
transformer, why you are setting CT configuration opposite to that of PTR configuration?
In star, star and
Sir,
delta,
there is
delta
a
cases.
lot of analysis that is required. Actually, if you are not connecting like that, if the fault is taking place outside its zone, also it will operate. That analysis is not required for you. You simply remember that CDs are oppositely configured in PTR configuration because to avoid the mal operation of the relay. To avoid what? Mal operation of the relay, we are connecting like that.
But
If
we
time
are
is there, I will analyze that in the last. Okay.
okay.
That is not required for you, but if time permits, I will see about it. Naga Tej.
హలో గుడ్ ఈవినింగ్ సార్
Good evening.
సార్ ఇప్పుడు బేసిక్ రిక్వైర్మెంట్ లో జస్ట్ డిఫరెన్స్ అనేది 180 degrees ఉండాలని చెప్పారు కదా సార్ ఇప్పుడు ఇక్కడ 30 అక్కడ 30 అంటే డిఫరెన్స్ అయినప్పుడు 30 మైనస్ 30 0
అంటే suppose if you reverse the coil 0 degrees can be directly converted to 180 degrees. No? ఇప్పుడు 0 degrees phase shift ని 0 degrees ఉంది సపోజ్ I1 I2 ఇలా ఉన్నాయి కాయిల్స్ ఇంటర్చేంజ్ చేస్తే మనకి ఇట్లా అయిపోతుంది కదా
అంటే అన్ని కేసెస్ లో పాసిబుల్ అవ్వాలంటున్నారు సార్
whenever 0 degrees is there you can make it into 180 degrees but if it is 30 degrees suppose if it is I1 and I2 ఇప్పుడు 30 degrees ఉంటే దీన్ని ఇంటర్చేంజ్ చేస్తే ఇది 180 degrees కాదు కదా
ఓకే సార్
అండర్స్టాండ్ మై పాయింట్
అర్థమైంది సార్ థ్యాంక్ యూ సార్
అభినందన్ గుప్తా
Sir, 6F.
Huh?
6F.
6F slide. What is your doubt?
Sir, in this, operating force should be greater than restraining force for operation.
Yeah.
Sir, by that, I'm getting lower region as operating region.
That's what no. This portion is removed by the restraining force. Actually, if you are not providing any slope, this will check simply zero value. No,
No, sir, you have written
this
NOP.
opposite will be the operating region. Okay. If the slope is zero, if there is no restraining coil, it will simply check I1 minus I2. If that is more than relay pickup value, the relay will operate. Okay.
Yes, sir.
This is
Sir,
relay pickup
sir.
value. Suppose if you are not providing any slope, that means if NR is zero, then it will check only this. This will be the operating region. Now by inclusion of this restraining coil, this portion is removed from operation.
Okay, sir. Sir, if we put F naught greater than FR, then NR and by N naught should be greater than this value.
That I will say, sir. While solving problems, I will explain about that.
So, sir, slope should be less than this value, no?
So here in this region, the bias should fall. The bias point should fall in this region.
Okay, sir.
Bias should be more than the slope.
Okay, sir.
Bias. Are you there?
Good evening, sir.
Good evening.
So in 19F, sir.
19F. What is your doubt?
So you're connecting, why are you connecting first star and then delta, sir?
Why you are?
Connecting star first and next delta, sir.
See here, question he has given power transformer is delta star. Okay.
Okay, sir.
This is the given data. Now we need to protect this transformer. So for protecting this transformer, we will connect the CTs on either side. Primary of the CT directly carries the line current. Okay.
Okay,
The secondary of the CT configuration is decided by power transformer configuration. Here power transformer is what connected?
the delta star.
So CT should be connected in what?
Star delta.
Star. So the power transformer is star. CT must be connected in
Delta.
delta. That's right.
Okay, sir. According to the table, sir.
Yeah, according to the table.
Okay, sir. Thank you, sir.
Sharath.
Sir, good evening, sir.
Good evening.
Sir, in that table, you said no, for delta star, you should nullify that 30 degree.
Yeah.
Sir, then there is no 30 degree phase shift for star and delta.
There is no not in case of delta and star both 30 degrees phase shift. But to overcome the mal-operation of the relay, if you connect in the same configuration, there is a chance of operation of the relay if the fault takes place outside its zone. To nullify that, we are connecting in this configuration. So that requires more analysis. For that, you should know the fault calculations. So that is not required as per your analysis of protection now. Just remember that PTR configuration is opposite to CT configuration.
Okay, sir. Okay. Sir, the CRO PDF is not uploaded, sir.
I will ask them. Otherwise, today at the end of the class, that is only 2 or 3 papers. You just take the screenshot. I will allow you.
Yeah, okay, sir. Thank you, sir.
Okay. Niharika.
Sir, good evening, sir.
Good evening.
Sir, actually, at starting of
Actually, at
Sir?
I'm not hearing your voice, sir.
starting of differential relay, sir.
Ah,
You told that the core saturation
yeah. In the last class, I heard no that.
falls outside the zone. So how they are related, sir?
How the?
How they are related, sir? Falls outside the zone and the core saturation.
How the?
How they sir, core saturation and the falls outside the zone, how they are related, sir?
How they are related means if the fault is taking place outside the zone and if one of the CT core is saturating earlier than the other, if one of the CT core saturates fast when compared to the other one, so what happens if the one of the CT core is saturating earlier than the other? So even the fault is not within the zone, if the fault is not taking place within the zone, but if you observe the magnetization characteristic, that is flux versus current characteristic. Suppose this is CT1 current and this is CT2 characteristic. Here CT2 is saturating for lower magnitude of current. Let it be some IX and IX dash. So this difference of the current will be resulted to the relay coil even when the fault is taking place outside the zone. Okay, that is a problem with the dissimilar magnetization characteristic. Okay.
So this can happen when within its zone also, no, sir.
If the fault takes place within the zone, the relay should operate, sir. If the fault takes place within the zone, the relay should operate. If the relay operates, no issue. If the fault is taking place within the zone. If the fault is taking place outside the zone, then the relay should not operate.
Okay, sir. Thank you.
Okay. Singham Mamata. Are you there? I'm not getting your voice.
Cleared, sir.
Huh?
Doubt cleared, sir.
Okay. Right, let us take a break. Come back at 7:20.
Hey, that's it. I'm good.
Welcome. After break, if audio and video is clear, I request the students to just raise the hand. If my audio and video is clear, I request the students to just raise the hand so that we can start our session. Right. Thank you. Now we have seen how to calculate the CD ratios. Now let us go for the next topic, that is transient behavior of transformer. Now let us analyze the transient behavior of a transformer. So if you consider an alternator, this is an alternator. This alternator is initially not connected to the transformer. This is the transformer. Okay. Alternator is not initially connected to the transformer. Here circuit breaker is open and this transformer is protected by a differential relay by connecting the CDs on both sides. Now we need to charge the transformer by closing the breaker. We need to charge the transformer by closing the breaker. Initially the transformer is not charged, but now the transformer is to be charged by closing the breaker. So now let us study the behavior of this transformer by closing the breaker at different situations. Now if you apply the observe the system voltage. System voltage is sinusoidal in nature. This is the voltage. Okay. Now as we know, the magnetizing component of current, I mu, the transformer winding is highly inductive in nature. So the magnetizing component of I mu lags the flux by magnetizing component of I mu lags the voltage waveform by 90 degrees. This is I mu waveform. Okay? This is I mu. Now the flux in the core will be in phase with what? The flux in the core will be in phase with this I mu. So the flux established in the core will be in phase with I. This is flux phi. Now let us observe the behavior of this transformer by closing the breaker at different instants. Now if you close the circuit breaker at this Vmax point, now at this Vmax instant, what is the flux demanded by the core? What will be the flux demanded by the core? 0. Okay. Flux demanded by the core is 0 at Vmax instant. Now let us observe. If circuit breaker closed at V maximum point, then what will be the magnetizing component of current? So magnetizing component, what will be the flux demanded by the core? It is 0. Flux demanded by the core is 0. So the initially the flux in the core will be also 0. Before closing the breaker, there will be no flux. Before closing the breaker, there will be no flux. Before closing the breaker, there will be no flux. So the flux demanded by the core will be 0. So there will be no transient. So I mu and flux will be in phase. So there will be no transient. If you close the breaker at what point? If you close the breaker at at Vmax point, if you close the breaker at Vmax point, there will be no transient in magnetizing component of current drawn. But if you close the breaker at voltage equal to 0 point, at voltage 0 point, what is the flux demanded by the core minus negative maximum here? If you observe, the flux demanded by the core at 0 crossover of voltage. At the 0 crossover of voltage, what is the flux demanded by the core? Minus phi m. At that point, the flux demanded by the core is negative maximum. So initially, what is the flux in the core? Flux in the core is 0. But suddenly it should develop how much flux? Phi m. It should develop phi m flux. So if the circuit breaker is closed at V equal to 0, suddenly it should develop maximum flux. Initially the flux, before closing the breaker, what is the flux? It is 0. So to develop that flux instantaneously, the transformer will draw heavy magnetizing component of current from the source. So which is a transient one. So there will be a transient in magnetizing component of current drawn by the transformer if the circuit breaker is closed at what point? Voltage 0 point. If the circuit breaker is closed at voltage 0 point. Okay. Now let us analyze like this. So if the circuit breaker is closed at Vmax point, if the circuit breaker is closed at Vmax point, the flux demanded by the core, is 0. So there is no transient. In I mu, that is magnetizing component of current, drawn by transformer. So if the circuit breaker is closed at Vmax point, the flux demanded by the core is 0, so there will be no transient in I mu waveform. So they are drawn by transformer. But if the circuit breaker is closed at a 0 crossover of voltage, the flux demanded by the core will be how much? The flux demanded by the core is phi maximum. So in order to develop that phi max instantaneously, the transformer will draw heavy unidirectional current from the source. Okay. So if circuit breaker closed at voltage 0 point, 0 crossover of voltage, the flux demanded by the core is by the core is phi maximum. The flux demanded by the core is phi maximum. In order to develop phi max instantaneously, sorry, in order to develop phi max at instant, the transformer draws heavy unidirectional current from the source. Unidirectional current from the source. It is a transient behavior. Okay. So what happens if the transformer is drawing heavy unidirectional current from the source? If the circuit breaker is closed, at if the circuit breaker is closed at current 0 point, then the flux demanded by the core is what? Phi maximum. So transformer will draw heavy unidirectional current from the source. So due to this, what happens? One of the CT core may saturate fast. This CT core may saturate, and the relay may operate. Okay. So due to this, due to heavy IMU current drawn from the source, what happens? One of the CT may saturate and operate relay, which is not desired. Here, which is not desired, because this is a transient behavior. As it is a transient, okay. As it is a transient behavior, that is not desired. You cannot say that you will exactly close at Vmax point or you will exactly close at voltage 0 point, because supply frequency is 50 Hertz. So the time period is 20 milliseconds. Supply frequency is 50 Hertz. That is 50 cycles per second. In 1 second, you will get how many cycles? 50 cycles. That means 100 zero crossovers you will get and 100 Vmax points you will get in 1 second. So you cannot get exactly Vmax you are closing or exactly voltage 0 you are closing. That is a transient. That depends on the fate of the operator who is closing that breaker. Okay. So that is a transient. So which is not desired. So how to avoid that? For that, if you synthesize this waveform, this IMU waveform is dominant with second harmonic component. Okay. So IMU waveform is dominant with the second harmonic component, because it is not symmetrical. It is unsymmetrical. Whenever it is unsymmetrical, it consists of both even harmonics and odd harmonics. It consists of even harmonics as well as odd harmonics. So it consists of both even harmonics and odd harmonics. Okay. So if you synthesize, it is dominant with what? Second harmonic component. So here, which is not here, due to that heavy unidirectional current that is drawn from the source, this differential relay should not operate. For that transient behavior. Here there is no fault. Just we are charging the transformer by closing the breaker. Okay. There is no fault. We are connecting the transformer to that network. During that, this transient may take place. Which is not desired for relay operation. So to avoid that, what we need to do? To avoid that, what we need to do? If you synthesize this IMU waveform is dominant with what? Second harmonic component. So to avoid the operation of the relay, to avoid the operation of relay, we use harmonic biased percentage differential relay. Harmonic biased percentage differential relay will be using which relay? Harmonic bias percentage differential relay. So just wait. Just wait, sir. Just wait a minute. Has been stopped. So we need to use which relay? Harmonic, sorry for disturbance. So to avoid this transient behavior of the transformer for relay operation, we need to use what? Harmonic biased differential relay. So what do you mean by harmonic biased differential relay? How it will be constructed? Now let us get. Suppose, what will you use? Here suppose this is an alternator. Here this has to be charging this transformer. What do you do here? Here we will be using harmonic biased differential relay. So we will be connecting the CTs on either side of this transformer which is to be protected. So here in between we will connect a relay coil. So we will be using biased restraining coil. This is NR by 2 and NR by 2. So here we will be using second harmonic restraining coil. So this is known as what? Harmonic biased differential relay. Which coil will be using here? Second harmonic restraining coil is used, and it is also known as what? Harmonic biased differential relay. Why second harmonic restraining coil is to be used here? Why second harmonic restraining coil is to be used? Because this IMU is dominant with what? Second harmonic component. Okay, that's why we will use what? Second harmonic restraining coil on either side of the relay coil. So that is about the transient behavior of transformer, and this is the analysis of transformer protection. Okay, this is the analysis of transformer protection. Now let us go for the next analysis, that is protection of alternator. Protection of alternator. So how the alternator is to be protected? Alternator is to be protected from which type of faults? Now let us analyze. So if you observe alternator consists of both stator and rotor. So alternator consists of stator and rotor. So if you observe the stator of the alternator, it consists of what? Three-phase windings. The stator of the alternator consists of what? Three-phase windings. So there will be three-phase windings R, Y, B. So these three-phase windings of the alternator are to be protected from two types of faults. That is, one is short circuit faults, and the other one is interturn faults. Okay. So the alternator consists of stator and rotor. The stator consists of three-phase windings. So these three-phase windings are to be protected from two types of faults: short circuit faults and interturn faults. So in stator protection, we will discuss about stator short circuit fault protection and interturn fault protection. And the rotor consists of field winding. So you should analyze the field winding protection, which is exerted with a separate DC source. Apart from this stator and rotor, we should also discuss about the protection of alternator from abnormal conditions. We should discuss the protection of alternator from abnormal conditions. So what are the abnormal conditions that the alternator may experience here? So we should discuss the protection of alternator from abnormal conditions, that is unbalanced loading. So we should discuss how the alternator is protected from unbalanced loading. Overloading protection we need to discuss. Overspeed protection we need to discuss. And loss of excitation we need to discuss. Loss of prime or input. Or mechanical input. So whenever you are saying the protection of alternator means we need to discuss these aspects in detail. Okay. So now let us go for the protection of alternator, stator winding of alternator from short circuit faults. So protection of stator winding of alternator from short circuit faults. How the stator winding of alternator is protected from short circuit faults? Now let us analyze here. So the short circuit fault protection is done by using percentage differential relay, because as said in differential relay analysis only I have said differential relay is used in protection of what? Alternator, transformer and bus bar. So we have completed transformer protection. Now coming to the alternator protection here. So protection of stator winding of alternator from short circuit faults we are analyzing here. Okay. So how the short circuit fault protection is done? By using percentage differential relay. So short circuit fault protection is done by using percentage differential relay. We will be using percentage differential relay for protection of alternator. Now if you observe the alternator winding, so the alternator stator consists of how many windings? Three-phase windings: R phase, Y phase and B phase. So the stator of the alternator consists of three-phase windings: R phase, Y phase and B phase. Now these three phases can be connected either in star or delta. But generally, if you observe, the three phases are star connected. Star connected. Generally, in most of the cases, the stator winding of the alternator is star connected, so that neutral can be grounded. The alternator neutral is generally resistance grounded to improve the transient state stability. The neutral is resistance grounded to improve the transient state stability. So this is the stator winding of the alternator to be protected from short circuit faults using percentage differential relay. So what are the basic requirements for differential protection? One is we require two similar electrical quantities to compare. In transformer, how we have implemented the protection, short circuit fault protection. There we have compared primary side current with secondary side current. But here there is no primary secondary. In case of stator winding, there is only one winding. So what do you need to do? We will compare the currents of stator winding of their respective phase on both sides. We will compare the currents on both sides of the same phase winding. by connecting the CTs. So we will connect the CTs on the same phase, R phase, Y phase, and B phase. So here we will be connecting the CTs and we will compare the currents. So here you should compare R phase current with R phase only, because if you compare R phase current with Y phase, so they will be out of phase by 120 degrees. We require 180 degrees out of phase displacement. That's why here we will compare the currents on the same phase windings. And the relay coil, where do you connect? Relay coil is connected exactly at the middle. Relay coil, where do you connect, sir? In the middle, you will be connecting the relay coil like this. Okay. Understood my point? So the short circuit, yes, sir. The short circuit fault protection is done by using percentage differential relay. How to implement the differential relay? By comparing the currents. By comparing the currents of same phase, by comparing the currents on either side of same phase winding windings, either side of same phase windings. Okay, by connecting the CTs, by connecting CTs. So we are comparing the currents on the same phase windings by connecting the CTs. Okay, during normal condition, the current in the CTs which are connected in the same phases will be same or different. During normal condition, the currents in the CTs which are connected in the same phases will be equal or not? Will be equal. So when the currents are equal, what will be the current to the relay coil? Zero. The relay will not operate. During normal condition, the currents in the same phase winding, on either side, it will be same. So in this CT and in this CT, the current will be same. So the relay will not operate during normal condition. But suppose if you consider a line to ground fault on Y phase, what happens? The current in the CT connected here will not be same as the current in the CT which is connected on the other side of that same phase winding, because the heavy current flows in this short circuited path like this. In this short circuited path, heavy current will flow, and the current in the CTs will not be same. That difference of the currents will be allowed through this relay coil, and the relay will operate for that fault. Okay, understood my point here? During normal condition, how the relay behaves? During normal condition, the currents in the CTs which are connected on same phases will be equal. The currents in the CTs which are connected in the same phase will be equal. So there will be no current. Through relay, and it will not operate. Okay. But whenever a short circuit fault takes place, what happens? Whenever a short circuit fault takes place, the current in the CTs which are connected in the same phases will not be same. The difference of the currents will be through what? Relay coil. The difference of the currents will be through relay coil. Okay. But during fault condition, the current in the CTs which are connected in same phase will not be same, and it results in current through relay coil, and relay operates for fault. Okay, understand my point here. So during normal condition, there will not be any current to the relay, but whenever the fault takes place, there will be current to the relay and the relay will operate. So whether this relay senses only grounded faults or both, whether the relay senses only grounded faults or both, it will sense both grounded faults as well as ungrounded faults. It can sense both. It will sense grounded faults as well as ungrounded faults. Line to line fault also it will sense. Or triple line to ground fault, triple line fault, all the faults it will sense. So can this type of configuration discriminate whether the fault is a grounded fault or not? Will this type of configuration discriminates whether the fault is a grounded fault or not? No. We cannot discriminate whether the fault is a grounded fault or not with this type of configuration. Okay. That means we cannot identify whether the fault is a grounded fault or not. Okay. So the relay will not use the discrimination for grounded faults. In order to have discrimination for grounded faults, we need to use restricted earth fault relay. We need to use which relay? Restricted earth fault relay. Restricted earth fault relay. So how this restricted earth fault relay will be constructed? Now let us see. So this is the alternator winding. So the alternator winding is 3-phase and it is star connected. Yes or no? Alternator winding is 3-phase and the neutral is grounded with resistance to improve the transient stability of the alternator. That you will be studying later. So here you will be using which relay? Restricted earth fault relay to discriminate whether the fault is a grounded fault or not. To have the discrimination for grounded faults, we use what? A restricted earth fault relay. So how do you implement this restricted earth fault relay? Now let us see. Here we will sum up the 3-phase currents. During normal condition, what is the sum of the 3-phase currents? 0. So here, in case of restricted earth fault relay, the sum of the 3-phase currents is being compared with the neutral current. So during normal condition, what is the neutral current? 0. And sum of the 3-phase currents will be 0. And there will be no current through the relay coil during normal condition. Okay. But when a grounded fault takes place, neutral current exists and there will be current through the relay and the relay will operate. This is known as what? A restricted earth fault relay. This is known as restricted earth fault relay. So here what we will compare? We will compare neutral current with sum of 3-phase currents. So here we are comparing the neutral current with what? The sum of the 3-phase currents in case of what? Restricted earth fault relay. So this will give the discrimination for grounded faults. Understand my point? This will give the discrimination for grounded faults. Okay. Now there are two areas where the problems, numericals are asked based on this short circuit fault protection. Now let us observe. Now let us consider solid grounded neutral and resistance grounded neutral We consider two cases. One is solid grounded neutral and resistance grounded neutral. And you consider the alternator winding. Same winding you consider. In one case, the neutral is solidly grounded. Means neutral is connected to ground without any impedance. That is solid grounding. Okay. Resistance grounding means the neutral is connected to ground with resistance Rn. Okay. Now, what is the behavior of these two types of groundings? How these groundings will affect the operation of the relay? Now, let us observe. Now, if you consider a short circuit fault taking place on very less number of turns. Short circuit fault is taking place on very less number of turns near the grounded neutral end. Short circuit fault is taking place on very less number of turns near the grounded neutral end in both the cases. So here, as the number of turns are less, the voltage induced is less. So this is the impedance of the winding ZFWD. Here also it is same ZFWD. Now what is the fault current here? IF1. How do you calculate IF1? V by ZFWD. Yes or no? V by ZFWD. This is the voltage induced. Here also the voltage induced will be same. Now here IF1 is less. IF1 will be less because the voltage induced less. The voltage induced will be less number of turns. IF1 is less, but relay senses and sense and operate for the fault and operate for fault. Okay, and relay senses and operate for the fault. Now let us observe the same case here. Let it be IF2. Here also the short circuit fault is taking place on very less number of turns near the grounded neutral end. But here IF2 is what? Now the fault current completed its path through this resistance V by ZFWD plus a neutral resistance that has been grounded. IF2 is less than IF1. So IF2 is not sufficient for relay operation. IF2 is not sufficient for relay operation. IF2 is not sufficient for relay operation. So IF2 fails to sense by the relay. So relay fails to operate. So what is your observation here? This is very important, sir. Listen carefully. When the neutral of the alternator is resistance grounded, and if the short circuit fault takes place very nearer to the grounded neutral end, the relay may fail to sense that fault because the fault current will be very less and the relay may fail to sense that fault. Okay. So what is your observation here? Due to resistance grounding of the neutral, certain portion of the stator winding is left unprotected. Okay. So in case of resistance grounded neutral, if the short circuit fault takes place, on very less number of turns, near grounded neutral and fault current will be less. And the relay may fail to operate, So which is desired or not? It is not desired, but relay is not sensing that fault. So due to resistance grounding of neutral, certain portion of the stator winding is left unprotected. So what is your observation? Due to resistance grounding of neutral, certain portion of stator winding left unprotected. So what is your observation? Due to resistance grounding of neutral, certain portion of the stator winding is left unprotected. The problems will be coming on like this. The problems will be coming on this area. How much winding is left unprotected? So what is the percent? How do you calculate? Percentage winding unprotected. So how do you calculate the percentage winding unprotected? How do you calculate, sir? The percentage winding unprotected is equal to relay pickup value multiplied with the neutral resistance that has been grounded divided by V phase voltage into 100 Here neutral resistance will be connected on primary side. Not here. Neutral resistance is on primary side. That's why this relay pickup value is to be calculated on which side? Primary side. This relay pickup value is to be calculated on which side, sir? Primary side. Okay. Now, this is the percentage of winding unprotected. Once you calculate the percentage winding unprotected, can we calculate how much winding is protected or not? Okay. So this is the peculiar behavior of this differential relay. Now let us discuss the protection of starter. Protection of alternator. So the next aspect is protection of alternator. So if you observe the alternator, it consists of what? Stator and rotor. The stator of the alternator consists of three-phase windings. So it may experience either short circuit faults or interturn faults. It may experience either short circuit faults or interturn faults. And rotor field winding must be protected. Apart from that, we should protect the alternator from abnormal conditions. What are the abnormal conditions that the alternator may experience? Unbalanced loading, overloading, overspeed, loss of excitation, and loss of prime or input. So all this protection must be done here. Okay. So protection of stator winding from short circuit fault. How the short circuit fault protection can be done for alternator winding? By using what? Percentage differential relay. Here you will be using percentage differential relay. How do you implement that? By comparing the currents on either side of the same phase winding. By comparing the currents on either side of the same phase winding. So during normal condition, the current in the CTs which are connected in the same phase will be same. But whenever the short circuit fault takes place, the currents will not be same. The difference of the currents will be through the relay coil and the relay will operate. Okay. So this is nothing but implementation of the differential relay. But this relay will not discriminate whether the fault is a grounded fault or not. This will not have the discrimination for grounded faults. You cannot identify whether the fault is a grounded fault or ungrounded fault. To have the discrimination for grounded faults, we require restricted earth fault relay. We need to use restricted earth fault relay. Here we will compare the neutral current with the sum of the three-phase currents. It will sum of the three-phase currents IR plus IY plus IP. During normal condition, what will be the neutral current? 0. Some of the three-phase currents will be also 0. Okay. So the relay will not operate. Whenever the grounded fault takes place, neutral current exists and the relay will operate. Okay. So now we consider solid grounded and resistance grounded case. So whenever the neutral of the alternator is resistance grounded, and if the short circuit fault takes place very nearer to the grounded neutral end, the fault current is not sufficient for relay operation. So the relay will not operate. So this is about resistance grounding of neutral. Generally, this formula is very important. How much winding is left unprotected? How much portion of the winding is left unprotected? Okay, that will be asked in the problem. All of you understood this one? No? Now, let us solve some problems. Based on this calculations. Just wait, sir. So, suppose if the problem is given like this, alternator winding is protected by percentage differential relay. Currents under fault condition are given in diagram. Calculate current through relay coil. If CT ratios are 400 by 5. So the question is given like this. So this is the stator winding that is to be protected, and this is protected by using a differential relay. Here CT connected 400 by 5. And the relay coil is connected in the middle. So here, suppose if it is given as 470 amperes, here it is 420 amperes, and these currents are due to fault. This network is experiencing some faults like this. So there is a fault in the alternator winding, and these are the fault currents given in the diagram. And what is asking to calculate? What is the current through the relay coil he is asking to calculate. So how do you solve this problem? How do you calculate the current through the relay coil? How do you calculate the current through the relay coil here? How do you calculate the current through the relay coil, sir? How can we calculate? Any idea? So this 470 or 420 are on primary side. So here you need to step down the current magnitudes. This alternator winding is experiencing short circuit faults. This is 470 amperes is on primary side. 420 amperes is on primary side. Now we need to calculate the currents on the secondary side. Relay coil you need to calculate. So here you need to calculate I1 and I2. Relay coil will carry I1 minus I2. So how do you calculate I1? 470 into 5 by 400. CT ratio is given as what? 400 by 5. So what about I2? 420 into 5 by 400. So what will be the current through the relay operating coil here? I1 minus I2. So I1 minus I2 is what? 470 minus 420 into 5 by 400. So how much do you get? This is 50 into 5 by 400. So if you simplify, how much do you get, sir? 50 into 5 by 400. So post the answer. 50 into 5 by 400. Calculate and post the answer. How much do you get? So what is the current to the relay operating coil here? What is the current to the relay operating coil? What is the current to the relay operating coil here? How much, sir? 0.625 amperes. 0.625 amperes. This is the current through the relay operating coil. Understood my point? So here, simple, sir. What is asking in this question? He has given the currents on primary side. He is asking to calculate the current to the relay operating coil. This was one of the previous questions that was asked in exam. Okay. Now, let us go for the next analysis. If the problem is given like this, stator winding of alternator, very important, sir. Winding of alternator is protected by percentage differential relay. Relay is pickup current of relay is 0.1 ampere and the slope provided is 10%. Currents under fault condition are given below. Check relay operates or not. Very important, sir. Check whether the relay operates or not. Very important model asked in exam. So now, how do you check? So observe here. So this is the stator winding of alternator, and it is experiencing a fault like this. Currents under the fault condition are given like this. Suppose same, if you take 470 amperes and here 420 amperes, you take 420 amperes, and here if the CT ratios are given like this, CT ratio is 500 by 5, here the CT ratio is also 500 by 5, and the relay coil is connected in the middle. CT ratio is 500 by 5. Okay. Now what is asking? Observe this question carefully. The stator winding of the alternator is protected by percentage differential relay. The pickup current of the relay is how much? 0.1 amperes. The slope provided by the relay is 10%. Currents under the fault condition are given below. Check the relay operates or not. Check whether the relay operates or not. We need to identify. So how do you check whether the relay operates or not? How do you check whether the relay operates or not? So first, let us observe what is the condition given. So here 470 amperes given, here 420 amperes given, and the CT ratios are given like this. So how do you find the solution? CT ratio given as 500 by 5, and here also the CT ratio that is given as 500 by 5. Now what is the current through the relay operating coil? First calculate. What is the current through the relay operating coil? First calculate I1, that is 470 into 5 by 500, that is 4.7 amperes. I2 is equal to 420 into 5 by 500, 420 into 5 by 500, 4.2 amperes. So what is the current to the relay operating coil that you will get? I1 minus I2. That is 4.7 minus 4.2. How much do you get? 0.5 amperes. Okay, 0.5 amperes. What is the pickup current of the relay given in the question? Relay pickup current given is how much? Relay pickup current is given as 0.1 ampere. So, but what is the current to the relay? Here 0.5 amperes it is flowing. 0.5 amperes it is flowing. Pickup current is 0.1 amperes. Whether the relay operates or not, 0.5 is greater than 0.1. Whether the relay operates or not. If it is an ordinary differential relay, the relay operates. If it is an ordinary differential relay, the relay will operate. But here, the slope is also provided. Slope is provided how much? 10%. Slope is provided how much? 10%. Now we need to include the effect of the slope. So here, how do you check that relay operates or not? So if it is an ordinary differential relay, suppose if it is I1 minus I2 and I1 plus I2 by 2. If it is not slope is 0, then if you simply check a relay pickup value, above this relay will operate. This is the operating region and this is the non-operating region. This is an ordinary differential relay. Here slope is what? Slope is 0. Here the slope is 0. But now in this case the relay will operate because 0.5 is greater than 0.1. But here the slope is provided. Slope is how much given? 10%. So I1 minus I2 and I1 plus I2 by 2. So here relay pickup value is given, RPV is given, and here the slope is given as how much? 10%. Due to the inclusion of this slope, this portion is removed from what? Operation. This portion is removed for operation. So this is the operating region and this will be the non-operating region. Now we need to check whether the point falls in the operating region or non-operating region. Now we need to check whether the point falls in the operating region or non-operating region. So how do you check? So minimum current required for relay operation. So how do you calculate minimum current required for relay operation? Relay pickup value is required. Plus the slope is to be overcome. Okay, plus slope into I1 plus I2 by 2. Okay. So now how do you include this? So relay pickup value is given in the question as how much? 0.1. Relay pickup value given as 0.1. Plus slope provided is 10%. 10 by 100 into here the what are the currents? 4.7 plus 4.2 by 2. 4.7 plus 4.2 by 2. So this is the minimum current required for relay operation. Can anyone calculate? 0.1 plus 10 by 100 into 4.7 plus 4.2 by 2 and pose the answer. Can anyone calculate this one and pose the answer? Can anyone calculate and pose the answer? .545. Okay. Now, what is the minimum current required for relay operation? 0.545 amperes. This amount of current is to be passed through the relay. But what is the current that has been passed through the relay? 0.5 amperes only. So 0.5 is less than 0.545 or not. So what is your conclusion? 0.5 amperes is less than 0.545 amperes. So relay fails to operate. Relay fails to operate. Okay, relay fails to operate. Understood my point? Now listen this carefully. I will repeat this question once again for your clarification. What is saying? The starter winding of the alternator is protected by percentage differential relay. Pickup current of the relay is 0.1 amperes. Relay is said to operate, slope provided is 10%. Currents under the fault condition are given below. Check whether the relay operates or not. So now first you calculate what is the current through the relay operating coil. ROC means what? Relay operating coil that you calculate. So how do you calculate? Here the current is I1, here the current is I2. Relay operating coil current is I1 minus I2. Okay. Now if the slope is 0, no doubt the relay operates. But here the slope is 10%. So minimum current required for relay operation. So how much you get? Relay pickup value plus slope into I1 plus I2 by 2. So then the relay will operate 0.5 amperes. But 0.5 amperes is less than 0.54 amperes. The relay will fail to operate. The relay will fail to operate. Okay. Now, if the next question is given like this, suppose, what is the slope that must be provided? What is slope to be provided? To be provided for relay operation. For relay operation. Next question is, what is the slope that is to be provided for relay operation? Means, how do you solve? Use the same equation. Minimum current required for relay operation is equal to relay pickup value plus slope that is to be calculated I1 plus I2 by. Here for 0.5 amperes the relay should operate. Relay pickup value is 0.1 given. Slope is to be calculated. Percentage slope by 100. Percentage slope by 100 into currents that are given are 4.7 and 4.7 plus 4.2 by. So from this you will get the percentage slope that is to be provided. So can anyone calculate what is the percentage slope that is to be provided for relay operation? Can anyone calculate the percentage slope that is to be provided for relay operation here? Calculate and post the answer, sir. Calculate and post the answer. Approximately how much? Slope that is to be provided is how much? 8.9. 8.9%. Okay. Slope to 8.9% slope is to be provided for relay operation. Okay. Now you get a slope that is 8.9%, greater than 8.9%, less than 8.9%. So here, when slope is equal to 8.9%, it is at verge of operation. Verge of operation. When it is greater than 8.9%, it will operate, or when it is less than 8.9%, it will operate. So here, observe, the point lies should fall in the operating region or non-operating region. When the slope is less than 8.9%, the relay will operate, or greater than 8.9. Whenever it is less than, it is in operation. When it is greater than that 8.9%, it will not operate. So if the options is one of the option, you may not give 8.9, you may give less than 8.9. That will be the answer. Okay. Other three options we can eliminate. Understood my point? Got my analysis here. Okay. So this is how you need to identify whether the relay operates or not. So when the slope is equal to 8.9%, it is at the boundary condition, at verge of operation. If it is less than that, it will operate. Less than that 8.9%, it will operate. If it is greater than that, it will not operate. Now, let us go for the next question. If the problem is given like this, Starter winding of alternator. Starter winding of alternator is protected by percentage differential relay. Is protected by percentage differential relay. Rating of alternator is 10 MVA, 33 kV, star connected. Relay is set to operate for out of balance current of 10% of full load current. 10% of full load current. So relay is set to operate for out of balance current of 10% of full load current. Okay. If the neutral is grounded through a resistance of 5 ohms, if the neutral is grounded with a resistance of 5 ohms, calculate the percentage winding protected. How much percentage of winding is being protected? Okay. So what is asking, the starter winding of the alternator is protected by percentage differential relay. The starter winding of the alternator is protected by percentage differential relay. The rating of the alternator is 10 MVA, 33 kV, star connected. Relay is set to operate for a out of balance current of 10% of full load current. If the neutral current is grounded through a resistance of 5 ohms, calculate the percentage winding that has been protected. So how do you calculate? So what is the given? 10 MVA, 33 kV, star connected. So what is the full load current? What is the full load current IFL here? S by root 3 times of VL. S is how much here? 10 into 10 power 6 by root 3 times of VL here. 33 into 10 power 3 you get. And the relay pickup value is 10% of this full load current given. That is, relay is set to operate 10% of IFL, no? 10% of IFL. 10 by 100 into this 10 into 10 power 6 by root 3 into 33 into 10 power 3. So what is asking to calculate here? Percentage winding protected he is asking to calculate. Percentage winding protected he is asking to calculate. So first calculate percentage winding unprotected. Percentage winding unprotected. I have given the relation. How do you calculate the percentage winding unprotected? Relay pickup value into neutral resistance divided by V phase into 100. Okay. So here relay pickup value that you have calculated 10 by 100 into 10 into 10 power 6 by root 3 into 33 into 10 power 3. Neutral resistance that is given is 5 ohms. Okay, 5 ohms into 100 divided by V phase. Phase voltage is how much? V phase is how much here? 33 into 10 power 3 is line voltage by root 3. Okay, so you will get the percentage winding unprotected. Okay. So can anyone calculate here? So if you simplify this 100 and this 100 will get cancelled out. Some 10 power 3 will get cancelled out here. 10 power 3 will be getting cancelled out. Some and this will get cancelled out here. You'll get the percentage winding unprotected. How much? Anyone calculated? Calculate and post the answer. Calculate and post the answer. Calculate how much winding is left unprotected. Calculate carefully. How much winding is left unprotected, sir? Check correctly, sir. Check correctly. Multiply that values correctly. Can you check correctly and post the answer? I request the students. Calculate and post the answer, sir. .45. Most of them are saying 0.45. So 0.45. This is the percentage of winding which is left unprotected. Okay. So once you calculate percentage winding unprotected, we can calculate percentage winding protected. Percentage winding protected. Percentage winding protected, that is 100 minus 0.45. How much you get? 100 minus 0.45. How much do you get, sir? 100 minus 0.45. What's the answer? So this portion of winding is left 99.5. How much? 99.55. Percentage of winding is protected. You should be careful while you are calculating this relations. Understood? So these are the models that are asked in previous examination with respect to what the protection of alternator. With respect to protection of alternator, okay? That is scatter winding protection. Now I will take the doubt session. If the students are having doubts, we can. If you are having doubts, you can raise the hand. If you are having doubts, now you can raise the hand, sir. If you are having doubts, you can raise the hand. I will give you the chance to ask. Ramchandran,
Sir, hello, sir.
ask your doubt.
Sir, in slide number 44, sir.
Slide number
44.
44. What is your doubt?
Sir, in this problem, the minimum current required is RPV plus slope into this I1 plus I2 by 2, sir.
Yes.
Sir, is this a formula or any logic behind it, sir?
There is no logic. Minimum current means this above this line it should get. That is nothing but I1 minus I2 only you need to calculate. Yes or no? That is equal to relay pickup value. That is this point plus slope multiplied with this value. Mathematical analysis only, no?
Okay, sir.
Okay?
Okay, sir. Thank you, sir.
Right. G. Vaishnavi.
Sir, in 43F, sir.
43. What is your doubt?
Sir, in this, can you say the formula how to calculate I1 and I2, sir? I forgot.
I1 is 470 given, multiply with 1 by CT ratio.
Yes.
Okay?
Sir, this 470 is primary current.
Primary side current.
Okay, sir. Sir, again, last 46F, sir. 46.
46. What is your doubt?
Sir, here, how did you say that if slope is less than 8.9%, then the relay will operate? If it is greater than 8.9%, the relay will
So if you observe here, I1 minus I2 and I1 plus I2 by 2. So initially we have the slope, this is RPV, and initially we have the slope of
10%.
10%. Now, here we got a condition. So this is a, if the slope is 10%, this is the operating region. Sorry, this is a not operating region.
Non-operating
This is
region.
operating region. Now, if you reduce the slope to 8.9%, 8.9%. Observe here. Now this, whatever this non-operating region becomes what? Operating region.
Operating region.
So if you go beyond this, it becomes non-operating region. If you increase the slope, if you observe 10%, for 10% is the relay operating? For 10,
No, sir. It is not operating.
it is not operating, no?
Yes, sir.
That's
Sir, again, can you again explain what is harmonic biased percentage differential relay? Sir?
harmonic bias or percentage differential relay you want.
Yes.
So if you observe here, this is the supply voltage waveform, okay?
Yes.
The magnetizing component of current lags the voltage by 90 degrees because transformer winding is highly inductive in nature, okay? This is IMU and flux waveform. If you close the breaker at Vmax point, what is the flux demanded by the core?
0.
0. So there will be no transient because initially the flux is 0 before closing the breaker, and whenever you close the breaker also there will be no transient, okay?
Okay.
But if you close the breaker at V0 point, what is the flux demanded by the core?
Maximum flux, that is minus
Maximum
5.
flux. So instantly it should develop how much flux? Maximum flux. At that instant it should develop maximum flux, okay? That particular instant it should develop maximum flux. So that is not for satisfying that condition, the magnetizing component is drawn heavily. That is from the source it will draw heavy unidirectional magnetizing component of current like this. Okay. So with this what happens, one of the CTs, to this CT only the magnetizing component will be there, yes or no? So this CT will get saturated, then the relay may operate even when there is no fault. This is a transient behavior, yes or no? For 3-4 cycles it will exist. After that it will not exist. Okay. So the relay should not operate. For that what we have done, we have synthesized this IMU waveform, which is unsymmetrical. So whenever the waveform is unsymmetrical, it consists of both even harmonics and odd harmonics. Okay. So if you synthesize this, it is dominant with second harmonic. Then what we have done? We have used the second harmonic restraining coil. What do you have used? Second harmonic restraining coil, so that the relay is biased for second harmonic. So it will produce the restraining force, so the relay will not operate. That is known as harmonic biased differential relay. Okay.
Okay. Here synthesizing means what, sir?
Synthesis means that any non-sinusoidal waveform can be expressed in terms of sinusoid. Okay. That is in signals and systems you will be studying about. Okay, right. Pradeep Kumar Jinnah.
Hello, sir.
Ask your daughter.
Why generation is in 3 phase only?
Huh?
Why generation is in 3 phase?
Generation is 3 phase.
Why, sir?
Why means for the same input, if you are going for single phase means there will be only one winding, no?
Yes, sir.
What is the difference between single phase, 2 phase and 3 phase system? Single phase winding, 2 phase winding and 3 phase winding. What will be the difference that you got? Single phase means only one winding. This is single phase. 2 phase means you will have 2 windings. This is 2 phase. 3 phase means you will have 3 phase windings. Okay. 4 phase means 4 phase windings you will be getting. So for the same mechanical input, that you are giving, the power that is generated will be more in case of 3 phase system. And if you go for 4 phase system, there is no appreciable increase in power. But if you are from 2 phase to 3 phase and single phase to 3 phase, there is an appreciable increase in power. So electrical power that has been generated. So they have decided to go for this 3 phase power generation. Okay. Srimatya S.
Sir, 46F, sir.
46. What is your doubt?
Sir, when it is less than greater than 8.5, it should operate, no, sir. Why it's not? Why you have written non-operating?
Suppose 10%, we have calculated already 10%, no? For 10%, 10 is
Yes,
greater
sir.
than 8.9%. Is it operating for 10%? 10 is greater than
Yes, sir.
8.9% or not?
Yes, sir.
Is it operating for that?
The relay is operating, sir. It's not operating.
10% it is not operating, no. 10 is greater than 8.9%.
Yes, sir.
Okay.
Okay, sir.
Okay.
Okay, sir.
Right. Sumitra. Vishnu Ajit.
Sir, same slide, sir. For slope greater than 8.9, it is already not operating. Then again, for slope less than 8.9, how it is operating, sir?
Slope 8.9.
For slope 8.9, with the logic you explained for the doubt, you said that it comes below the 10% region in non-operating, so it is not operating for greater than 8.9.
Sir, observe here. This is I1 minus I2 and I1 plus I2 by 2. Okay. So this is relay pickup value. Understood my point?
Yes, sir.
So suppose this is the slope 8.9%. Okay.
Okay, sir.
Now this is the operating region and this is non-operating region.
Okay.
Now suppose you should make the slope as some 10%.
Okay, sir.
Actually the point lies here.
Yes, sir.
Slope as 10%. Now it behaves non-operating region or operating region?
With respect to 10% slope, sir.
With respect to 10% slope only you should say, no?
Then it is not operating.
Then what is it?
Then for less than 8.9 also it is not in NOP region of 10.
Suppose slope 2%. It is in operating region. No, it is not.
Sir, this actually, sir, this is operating, okay, sir. But it is again less than 10%, no, sir. It is
less than.
I mean, it comes in the this operating region of slope 2% comes in the non-operation region of slope of 10%, no, sir.
Why when you are discussing about 2%, why you are bothering about this 10%?
But in that case, then in the case of slope 8.9, when we consider the greater part, that time we saw for 10%, no, sir.
Sir, slope of 8.9%, this is the operating region and this is the non-operating. Okay.
Okay, sir.
For 10%, this is the operating region and this is non-operating.
Okay, sir.
So this is not operating. Understood?
Almost, sir. And sir, one more, sir. This first problem you explained this for alternator winding.
So what is your doubt there?
Sir, in that we found out I1, we found out I2, then we are finding out the relay. Relay operation current. Again, there we are multiplying by the current transformer ratio. Already I1 and I2 have been transferred in terms of secondary. Then why should we again multiply it by 5/400?
Where?
That first problem. I think no, sir. Next. Not this one, sir. The answer came as 0.625 amps.
Where, sir? This one.
Yes, sir. Here also you have multiplied below into 5/400 again.
Where?
The IROC is
I1 470 into 5/400. I2 is 420 into 5/400. I1 minus I2 is difference of.
So my bad, sir. Sorry, sir.
Okay.
Thank you, sir.
Vikram Pujjar.
Good evening, sir. Sir, 24.
24.
Sir, I have a general doubt. Like over here, it is given that power transformer is delta to Y connected, delta to star, and the rating is 132 by 33. So when such a rating is given, that 132 by 33 or some other like 66 by 11, so are these line to line voltages, or are these line or phase voltages depending on the configuration?
Remember here, until and unless specified, the values that are specified are line values.
Irrespective of configuration, sir?
Irrespective of configuration, the ratings that are specified for any alternator, transformer, transmission line, whatever in power system network, the values that are specified will be line values only by default.
Okay, sir.
Okay.
Yes, sir. Got it.
Rudviraj,
Hello, sir.
ask your doubt.
Sir, that question is there, na sir, slope value question.
What is your doubt here?
Sir, there you gave statements in opposite direction, but explaining the logic in different direction. Means when slope is less than 8.09, can you open it? This slide only. So slope, if you draw a slope diagram, if slope is less than 8.9, it should be in upper part.
Sir, this is I1 minus I2.
It should be in down part.
Okay. This is slope 0. Okay.
Okay, sir.
0. Now, this is slope
8.9.
So this is the operating region and this is non-operating. Suppose if you make slope
But at the side
5%. Okay. So this will be in operating region and this will be in non-operating. Is there any effect of that?
No, sir.
No, but
sir, what I am saying is you gave statements, na sir. That's
if the slope is 15%, this portion is non-operating region and this portion will be operating. That means the point is lying on this.
Okay.
Understood?
But you gave statements at the left. You gave statement, na sir. Those are in opposite way of your explanation.
Where statement?
On screen, na sir. On screen you wrote, na sir. On screen you wrote slope greater than 8.9. On screen only it is showing, na sir, slope greater than 8.9.
When the slope is greater than 8.9%, the relay will operate or it will not operate.
Slope greater than 8.9 means point falling above the line, na sir. Relay will operate.
Sir,
point will fall above the line, sir.
You do one thing, okay? For the same problem, you take slope of 12%, okay? Greater than 8.9%, no? And you check whether the relay operates or not. And you take a slope of 5% and check whether the relay operates or not, okay? That is the assignment for you for tomorrow's class, okay? What you do is take slope of 12% and check whether the relay operates or not. And take a 4% or 5% and check whether the relay operates or not. Okay.
Sir, but for that current will change, na sir. Minimum current required for that relay.
Which current? The minimum current required for that relay will change, no doubt. So what happens?
Then how can we compare all these things?
For that fault, relay operates or not, you check, no? Here I am bothering about this fault.
Sir, one more point is understood, sir. I will do homework. And one more point is fault relay. Sir, alternator protection earth fault relay is there, na sir? Restricted earth fault relay.
Okay. What is your doubt?
Sir, there after that you have explained about solid ground and neutral resistant ground differences will be you have explained.
Okay.
So this will applicable for restricted earth fault relay or the before that normal protection you have said, na sir, for line current and
restricted earth fault relay.
Okay, this is only applicable for restricted earth fault relay. Okay, sir. And, Sir, can you go for Buckard's relay?
Huh?
Buckard's relay, sir. Buckard's relay.
What is your doubt, say?
Sir, in that sequence of operation will be in which way, sir? Means top switch we have given for alarm circuit, bottom switch we have given for trip circuit. Whenever gas will start forming, both switches operated simultaneously or at different times.
First, actually, the trip signal has more importance. No, that's why first trip signal will be initiated.
Okay.
Then with some delay, alarm will be.
Okay, sir. That's it, sir.
Sunil.
Hello, sir.
Ask your doubt.
In the last problem of PTR, sir.
Last
PTR,
problem.
last PTR, sir.
CT ratio calculate.
Yes, sir. It's a 26 or 27, sir. Page number.
This one. This one only.
Yes, sir.
What is your doubt?
Sir, in that the pilot wire carries 5√3 current, sir. How, sir?
This one 5√3.
Yes, sir.
Here CT ratio given, no, LT side 500 by 5. If this is 500 amperes, this phase current will be 5 amperes. Always the secondary side must be phase current here.
Yes, sir.
Okay. We have solved the remaining problems also. No? In this here, how IY you have taken 5/√3. IY is phase current or line current?
Base current, sir.
Here also this 5 amperes should be phase current only. No, here CT ratio is not minor.
Okay, sir. Okay.
Okay.
Yes, sir. Got it.
Pragati Jallu.
Yes, sir. 1F. So in the yesterday's class, you told that when the fault occurs outside the zone due to the core saturation, the relay will operate in differential relay. So for that, we are using percentage differential relay.
Okay.
I was wondering, like in percentage differential relay, even if the fault occurs outside the zone, how is it gonna?
Here we are
not affect
developing
core
the
saturation?
additional restraining force here.
Okay.
By connecting this additional restraining coil, additional force is developed to oppose the operation of the relay.
Okay. Whenever there is a core saturation occurs, even if there is a current, the restraining coil will oppose it.
Even it is saturating, here it is I1 plus I2 square restraining force, but operating force is I1 minus I2 square.
Oh, okay, okay. And sir, we are using this CTs which are to be connected in opposite configuration to nullify the 30-degree phase shift.
Yeah.
30-degree phase shift only occurs in delta Y or Y delta.
Yeah. Yes.
Then why are we using the CT transformation?
Actually,
for
what happens is if you are using, even in case of star and delta, if you use the same configuration, the problem is if the fault is taking place outside the zone, also sometimes the relay may sense that fault. So to avoid that, we are going for opposite configuration.
How it is gonna sense?
How it will happen means for that the lot of analysis is required. At the end, if time persists, I will go.
Okay. In protection of stator winding of alternator, sir, there is this restricted F4 relay which we are using.
Yeah.
You told that it is gonna sense the neutral current, but in triple LG fault, anyway the neutral current is equal to 0, no sir?
In triple LG fault?
It's a balanced fault and the neutral current will be 0, sir.
No. In triple LG fault, triple LG and triple L fault, fault CBRT will be same. But whenever compared to line to ground, double line to ground, the fault CBRT is not the same.
So we are not able to differentiate triple L and triple LG fault.
Triple LG fault will not be discriminated because that is a balanced fault that will not have it.
Okay, last one. This we are using separate for short circuit fault and interturn faults in transformer, no sir?
Yeah.
is interturn faults severity less than short circuit faults, sir?
Interturn fault severity will be less than short circuit fault severity. But what happens is this interturn fault is cumulative. That means it is go on increasing. Suppose first 1 or 2 turns get short circuited, then other adjacent turns will be damaged. Likewise, it will become total damage.
Okay. So in practical power system network, we are gonna use all this percentage bias relay, Buchholz relay, everything in the power system.
Yeah, we will be using this percentage bias.
Like all kinds of relay will keep separately for interturn fault and short circuit fault for every.
Yeah. Interturn fault protection separate. Interturn fault protection, I have shown no Buchholz relay. It is located between main tank and conservative tank.
Okay, sir. Sir, in yesterday class, I have a doubt.
What doubt?
And I asked you through WhatsApp. I don't know, like I didn't get a response. In journal protection scheme, we have these 3 units like U1, U2, U3.
Okay.
If we are gonna use reactance relay in this journal protection scheme and assume the set time relay for T1 equal to 0.1 and T2 equal to 2 seconds and T3 equal to 3 seconds.
T2 equal to how much?
3 seconds. Like it will increase, no sir.
T1 how much?
0.2 seconds.
Okay. T2?
2 seconds.
Okay.
And T3 equal to 3 seconds.
Okay.
So yesterday you have considered this particular section like fault 1 happens, 2 happens, 3 happens.
Okay.
So in that particular thing, if fault 3 occurs, like which relay is going to sense and how much time it is going to take?
Fault 3 is sensed by unit 2, no?
Okay, I mean yesterday you told that it will sense it, but it is going to operate only after unit 3 like activates or something.
R2 is operating.
Sorry, sir.
I will come to that doubt like this. Okay, just wait. We'll take that separate. So your doubt is in zonal protection scheme.
Yes, sir.
So this is first section, this is second section, this is third section. This first section is protected by R1, second section by R2, third section by R2. Okay. The unit 1, this is zone 1 of R1. This is zone 2 of R1. This is zone 3 of R1. Okay. So this is zone 1 of R2. This is zone 2 of R2. Like that. So here, whenever the fault takes place in this first F1, it is falling under zone 1 of R1, it is instantaneous and it is operating. Okay. This
Yes,
F2 is censored by this unit 2 and it will operate. Actually, this F3 previously it was censored by R1 as well as R1. But here also, if you observe, it is censored by both zone 1 of R1 and zone 1 of R2 and zone 2 of R1. But here zone 1 of R2 will be of what mode of operation?
Instantaneous.
Instantaneous. But this is with
some delay.
So first relay which is operating is what? R2. No?
Yes, sir. That I got. But the point is, for reactance relay, you told that it is required to be operated along with starting unit. That is more relay.
Starting unit, yes or no? But here, if you observe the character,
yeah.
Suppose this is a Z3, no? That unit 3 includes up to this point. Okay? So whenever this fault F3 falls, it observes both the units here. Okay? This is the first.
So the relay is going to operate after 3 seconds.
Yeah. Which relay?
Reactance relay.
No. This relay will sense. This more relay will sense first. But here there is a time delay, no? Even though it is sensing, we are intentionally providing a delay of 3 seconds.
Yeah.
But it is simultaneously censored by X2, no?
Okay, it senses and it reacts.
It senses but reacts after 3 seconds. But once it is sensing, it is allowed to operate.
So the fault will be cleared by R2 after 3 seconds.
Actually, the circuit you can visualize like this. What happens is this M3 is there, no? This M3 will be coordinated with a timer, okay? And here this M3 and you can say it as X1 will be directly operated, and you can say it as M2 with X2 with certain delay that will be introduced, okay? And M3 with another delay 2 will be introduced. Understood my point?
Okay.
So once M3 is sensing, this timer will be activated, okay?
Okay.
And once M3 is sensing, X1 is allowed to operate. Once M3 is sensing, X2 is allowed to operate after delay. M3 is allowed to operate after the delay of T.
Okay. So, I mean, like the reactance relay is taking more time. Like after 3 seconds, it is going to sense it.
After 3 seconds, not sir. Once M3 is sensing, timer will be activated, no? Timer will be activated. Suppose this is 2 seconds and this is 3 seconds. Here M3 is sensed and X2 is also sensed. It will operate for 2 seconds.
Oh, okay, okay. Got it, sir. Thank you so much, sir. Thank you.
Okay, right. We'll close the session for today. If you have any doubt, you can contact me on this number, or you can mail it to us.